Mr. Clelland here for Clelland Maths. This is your Advanced Higher Maths 2025 Ultimate Exam Prep video. It's going to go through every single topic, question by question, topic by topic. Hopefully you find it useful, and if you do, just give us a like and a subscribe. If you want more content, if you want some extra help with your exams, then why don't you join this channel? It is only £4.99, and as in return for joining, you will get an exclusive members-only live stream on the day before the exam on the 11th of May at 7 PM. If you want to join in, click and pay your £4.99. Clelland Maths is sponsored by Locus, the educational publisher for Scotland. They offer viewers of this channel a massive 30% discount. Just use the discount code ClellandMaths at locusscotland.co.uk. The practice question books go all the way from level 3 to advanced higher and include National 3, 4 and 5 apps as well, so you can get any book you need for your studies. These are an excellent resource with questions on every topic and contain work solutions so you can see how the marks are awarded. As you go through the book, the questions get increasingly difficult, so by the time you finish your book, you'll be ready for your exams. Usually £9.99, just use the discount code ClellandMaths to get 30% off that. Link down below. Advanced Higher Maths 2023 Paper 1 Question 2, Express this in partial fractions. So we've got a repeated root on the bottom, so the form is a over x plus 3 plus b over x minus 1, but then you plus c over x minus 1 squared because of the repeated root. So let's equate the numerator, so times in this one by x minus 1 squared, we get a x minus 1 squared plus b, that needs to be times by x minus 1, but x plus 3 as well, and then c just has to be times by x plus 3, and that equals our numerator of 3x squared minus x minus 14. And now we just pick numbers for x to eliminate to get a, b and c. So when x equals 1, we can see that a and b disappear because 1 minus 1 is 0, to leave us with 1 plus 3 is 4c. And that's going to equal the right hand side of 3, take away 1 is 2, take away 14 is minus 12. And then therefore we get c is equal to minus 3. Can do the same trick for x equal to minus 3 to get rid of these two. So when x equals minus 3, we get minus 3 take away 1 is minus 4 squared, which is 16a. And on the right, we get 3 3s are 9 times 3 is 27. Plus another 3 is 30, minus 14 is 16, which gives us down to a equals 1. And now we can just pick any number we want. Let's pick 0. So our left hand side, being very careful, we get 1 squared is 1a. So I'll just write down a. And then we get minus 1 times 3 is minus 3, so minus 3b. And then we get 3 times c, which is 3c. And on the right, we get minus 14. So a is 1, minus 3b, and then 3 times minus 3 is minus 9, equals minus 14. So 1 minus 9 is minus 8, so we get minus 3b minus 8 equals minus 14. So minus 3b equals minus 14 add 8, minus 6. So b is equal to 2. So to answer our question, we've got 1 over x plus 3. And then your b was 2. So 2 over x minus 1, and then your c was minus 3, so minus 3 over x minus 1 squared, and we're done there. Express in partial fractions, 3x squared minus 3x plus 5 over x squared plus 5. So remember that means 3x squared minus 3x plus 5 over x squared plus 5 must equal a over x plus bx plus c over x squared plus 5. So that implies that the numerator 3x squared minus 3x plus 5 must equal, making this denominator cross multiplication is the simplest way, x squared plus 5 plus bx plus c times x. So let's just put in some numbers for x and work out our a, b's and c's. So let's say at x equal to 0, that implies we get 5 on the left equals 5a on the right, which implies a just equals 1. Okay, let's do x equal to 1. That implies on the left we get 5 again. And on the right hand side we get 1 plus 5 is 6, so 6a, and plus b plus c. But we already know that a equals 1, so that means we've got b plus c just equals minus 1. And then we need to find another one, so let's try x equal 2 this time. So that implies our left hand side is going to be 2 2's is 4 times 3 is 12. 12 minus 6 is 6 plus 5 is 11. So we get 11 equals 9a plus 2 times 2 is 4, so 4b plus 2c. But we already know that a is 1, so 9 times 1 is 9, so that gives us 2 on the left, equals 4b plus c, 2c. Dividing through by 2, we get 2b plus c equals 1. And we already know as well, though, that b plus c is minus 1, so we can just take them away from each other. And we get b equals to 2, which implies that c equals minus 3, because 2 becomes minus 3. So then, just to answer our question then, 3x squared minus 3x plus 5 over x squared plus 5 equals a over x, so 1 over x, plus bx plus c over x squared plus 5. Paper 1, question 1. Differentiate the form with respect to x, y equals cot 3x, and y, f of x is 5x, 4x minus 7.5. So part A, we've got the chain rule to do here, so we've got the y by the x, and you check the start of the exam paper, and cot goes to cosec. So I've got cosec squared 3x, and then I times by that 3. So 3. So minus 3 cosec squared 3x. Just check that at the start of the exam paper. Cot goes to minus cosec squared. So yeah, that's fine. Right, part B, f of x is 5x, 4x minus 7.5. So a nice little product rule here, f dash x. So we've got uv. So it's v u dash, remember. So u dash is 5, and we'll just keep v as it is, plus u 5x times v dash, so that's a half, 4x minus 7 minus a half, and 8 times by the derivative, which is 4. So tidying that up as much as we can or want to, we've got 5, 4x minus 7 to the half. Half of 4 is 2, 2 5s is 10, so 10x, 4x minus 7 to the minus a half. And I think you'll probably get your marks there. You could probably go one step further and take 5, 4x minus 7 to the half out as a common factor. But you can end up with a messy thing in the middle. I'll show you what I mean. I could do 5, 4x minus 7 to the half, or even to the minus a half if you prefer. And that would give me just 1 plus 2x, and I would have 4x minus 7 still. And then I want to have a number which is minus 1. Half minus 1 is minus a half. So yeah, that's a little bit messy. So I think part B is fine. SQA Advanced Higher Mathematics 2023, paper 1. full solutions. SQA Advanced Higher Maths 2023 Paper 1 Question 1. Given y equals 7x tan 2x, find the y by dx. So we've got a function of u and v. So u dash would be 7 and v dash, from the start of the exam paper, tan goes to sec squared x. So that's 2 sec squared 2x. So dy by dx equals vu dash plus uv dash. So we've got tan 2x times 7 plus 7x times 2 sec squared 2x. 7 tan 2x plus 14x sec squared 2x. And we're done there. SQA Advanced Higher Maths 2024 Paper 2 Question 1. Given the y equals 7 sine 7x over 1 plus x squared, find the y by dx. So we're going to use the quotient rule. So we've got the y by dx is equal to v, 1 plus x squared, u dash, sine becomes cos, so it's 7 cos 7x, vu dash minus u, sine 7x, v dash, well that's just times 2x, all over v squared, which is 1 plus x squared, all squared. Tidy that up a little bit, but it is only worth 2 marks. So I've got 7, 1 plus x squared cos 7x minus 2x sine 7x all over 1 plus x squared and squared. And let's see if we can do anything else with that. I'm happy to leave it like that, so I'm done there. So question 1 says, given that y equals 1 minus 3x over x squared plus 4, find dy by dx and simplify your answer. And then part B of that question, given that f of x is cosec 5x, find f dash x. So the first question is just a quotient rule question, and the second question is just a trigonometric function, which we can use to start the exam paper. So 1a, the y by dx is 1 minus 3x over x squared plus 4. So I'm going to let u of x equal 1 minus 3x. So that means u dash of x is minus 3. And I'm going to let v of x equal x squared plus 4, which means v dash of x is 2x. And if you remember our quotient rule for our function, u of x over v of x is u dash v minus v u dash all over v squared. V's all been a function of x. So substituting everything we've got in, that gives us minus 3 x squared plus 4 minus 2x 1 minus 3x all over x squared plus 4 all squared. So that equals minus 3x squared minus 12 minus 2x plus 6x squared over x squared plus 4 squared. That gives us 3x squared minus 2x minus 12 over x squared plus 4 all squared. And we're done. Okay, question B says, given f of x is cosec 5x, find f dash x. Well, if we go to the front of the exam paper, it will tell us that standard derivative, which I've copied here, of cosec x is minus cosec x cot x. So we know f of x, so we can work out f dash x straight away. So that gives us minus 5 cosec 5x cot 5x. And we're done there. Maths 2024 Paper 1 Question 7. A curve is defined by this equation. Use implicit differentiation to find the y by dx. So we've got x squared y. So that is the product. So I'll do v u dash, so y times 2x, plus u v dash, x squared y, so it becomes the y by the x. Similarly, for 4xy squared, I'll call 4xv, and then vu dash y squared becomes 2y, the y by the x, and then plus vu dash y squared times 4x is 4, and that equals the derivative of minus 32, which is nothing. So tidying that up, we've got 2xy plus x squared dy by dx plus 8xy dy by dx plus 4y squared equals 0. Dy by dx here, and I've got x squared plus 8xy, and that equals minus 4y squared minus 2xy. And then we can just divide by whatever the y by the x is times by. So that means that the y by the x is minus 4y squared minus 2xy all over x squared plus 8xy. And we're done there. Only one stationary point. Find the coordinates of the stationary point. So the y by the x equals 0 for stationary points. So part B, stationary points, the y by dx equals 0. So if the y by dx equals 0, and that's our expression, then that times that is 0, so the top is just 0. So 4 minus 4y squared minus 2xy is 0. So let's see if we can take a common factor. Well, we can take 2y out. So that gives me minus 2y and minus x. So that means that 2y equals 0 or minus 2y minus x equals 0. So y equals 0 or x equals minus 2y. But it can't be that one, simply because there's only one stationary point and y is greater than 0. So it is the other one. So if x is minus 2y, we can just sub it back into the original equation. So we've got x squared y plus 4xy squared equals minus 32. So minus 2y squared times y plus 4 times minus 2y times y squared equals minus 32. So 2 twos is 4, so that's 4y cubed. 4 twos is 8, so that's minus 8y cubed, and that's minus 32. So minus 4y cubed is minus 32. So y cubed is minus 32 over 4. 4 eighths is 32. So y must be 2, because 2 times 2 times 2 is 8. If the y is 2, then x equals minus 2 times 2, which is minus 4. So the stationary point equals minus 4 and 2. And we're done there. SQA Advanced Higher Maths 2023, Paper 2, Question 4. Calculate the gradient of the tangent to the curve with the equation x squared y squared minus 2y equals sine 3x at the point 0, 0. So gradient of the tangent means derivative, so we need to differentiate this function. So let's see what we've got, x squared y squared, so we can implicitly differentiate it. So looking at our left-hand side, we've got y squared times 2x plus x squared times 2y, and that becomes the y by the x. And that's just using the product rule in the first one. And then the second part, minus 2y, becomes minus 2 the y by dx. And then our right-hand side, sine 3x becomes 3 cos 3x, I suppose. So then we can just tidy that up to get an expression for the derivative, the y by dx. So moving everything across, it isn't got the y by dx in it. We get x squared 2y the y by dx minus 2 the y by dx equals 3 cos 3x minus y squared 2x. Taking the y by dx as our common factor then, we get x squared 2y minus 2 equals 3 cos 3x minus y squared 2x, and therefore the y by dx is equal to 3 cos 3x minus y squared 2x over x squared 2y minus 2. So at 0, 0, dy by dx is equal to 3 times the cos of nothing minus, well, that'll just be 0 over 0 again, minus 2. Tidying that up, the cos of nothing, of course, is 1. So we get 3 over minus 2, or minus 3 over 2 as the gradient of the time to the curve at point 0, 0. And we're done there. SQA Advanced Higher Maths 2023, paper 2, question 10. A curve is defined by y equals x to the 5x squared, where x is greater than 0. Find the y by dx in terms of x. So let's start off with y equals x to the 5x squared, which is an exponential. So we can take the log of both sides to start with. So log y equals log x to the 5x squared. We can separate out our right hand side, so log y equals 5x squared times log x, and then we can differentiate both sides. So differentiating the left hand side, log y becomes 1 over y, that is the y by dx because we're differentiating implicitly, and the right hand side is a product. So we've got vu dash plus uv dash, so v is log x times u dash is 10x plus u, which is 5x squared, times v dash, which is 1 over x. And we'll just need to tidy it all up. So 1 over y, dy by dx is equal to 10x log x, just to make that neater, plus 5x squared over x is just 5x. Now we can times through by y. So that means that the y by dx is equal to y times 10x log x plus 5x. But we know what y is. Y is x to the 5x squared. So we're going to sub that back in for y. So the y by dx is x to the 5x squared 10x log x plus 5x. So the y by dx. Now we can take out more factors here. So we've got 5 is a common factor and x is a common factor. So we can take 5x out, I suppose. I'll write that out in long way. So I've got 5x times x to the 5x squared. So I've took 5x out. So that leaves me with 2 log x. And it also leaves me with plus 1 in the brackets. Remember, in maths, our most simple answers are factorised answers. So I'm going to try and leave it as factorised. So dy by dx. So I've got 5x times x to the 5x squared. So I can add the power. So that's just a power of 1. So that's going to be 5x squared plus 1. So I've got 5x to the 5x squared plus 1. I'll put that in brackets for clarity. And that's times by 2 log x plus 1. And that's as simple as it's going to get. So I'm done there. SQA Advanced Higher Maths 2024, paper 2, question 6. A curve is defined parametric whereby x equals t squared and y equals 4t log t, where t is greater than 0. If we simplify the expressions for dy by dx and d2y by dx squared, let's just start with the first one. A, dy by dx, dy by dt, dt by dx. So I need to work out those things. So dy by dt, where are we? There we are there. So it's a product, so it's v, u dash, so that's log t, and u dash is 4, plus u, v dash log t becomes over t. Simplify that, we get 4 log t plus t, plus 4 even, what an idiot I am. 4 log t plus 4. Now we could simplify that further by putting it in brackets, but I'll leave it like that right now in case I need it outside. I'll put it back in later. So now I'll just do my dx by dt to get my dt by dx. Dx by dt is just 2t. So now I can work out my dy by dx. I've got 4 log t plus 4. And it's times by dt by dx. So it's divided by 2t times 1 over 2t. So now we can just divide through by 2 to get 2 log t plus 2 over t, which is 2 log t plus 1 all over t. And I don't think I'm going to simplify it any further than that. Part B, d2y by dx squared. Well, I've got the y by dx, let's put that up here, in terms of t. So you're going to do d by dt of the y by dx. But then I'm going to have to eliminate that t, so times the t and then by dx. Why dx? Because I want d2x. So there you are. So that is the second derivative. So I'm going to use the product rule, quotient rule. So v times u dash. So 2 log t. Log t goes to 1 over t. So that's 2 over t, and plus 2 goes to nothing. So vu dash minus u v dash is 1 all over v squared, which is t squared. And now I need to times by dt by dx, if you can remember what it is. dx by dt is 2t, so the t by dx is 1 over 2t. So that's what we need to do. And then we need to somehow simplify this. Well, let's hope it's nice. So that gives me t over t is 1, so that's 2. Watch for your signs here. Minus 2 log t, and it's minus 2. All over t squared times t is t cubed, 2t cubed. So obviously you can see the 2's cancel. So that gives me, dividing through by 2, they're gone. 2 divided by 2 is 1, so minus log t over t cubed. And I think I'll leave it like that. And I'm done there. Question 11. A curve is defined parametrically, which has the following properties. X is inverse tan of 2t. The y by dx is 6t, 1 plus 4t squared, and we've got y equals 5 and t equals 1. Okay, this is very interesting, but recall parametrically, if I write this, the y by dx, that's just the y by dt times the t by dx. Now, let's start off by looking at dx by dt then, which means we can get dt by dx. So looking at dx by dt, we know that first of all, x is the inverse tan of 2t. So we need to differentiate the inverse tan of 2t. So let's say x equals inverse tan of u, where u equals 2t. Then obviously dx by du, using your formula sheet if you have to, is 1 over 1 plus u squared. And the u by dt just equals 2. So dx by dt is going to be dx by du times du by dt. So that's 1 over 1 plus u squared times 2. So we've got dx by dt is just 2 over 1 plus 2t squared, so 4t squared. So that implies that dt by dx is what we're trying to find out, is 1 plus 4t squared over 2. So remember, the y by dx is simply the y by dt times the t by dx. But we already know what the y by dx is. It's given to us in the question. That's 6t, 1 plus 4t squared. So we've got the y by dt times 1 plus 4t squared over 2 equals 6t, 1 plus 4t squared. So we can imply that the y by dt is simply 6t, 1 plus 4t squared. Dividing by a fraction is the same as times and by its reciprocal, so 2 over 1 plus 4t squared. And you should be able to see that these cancel, and therefore the y by dt is just 12t. So we can integrate to find y now in terms of t. So y is going to be the integral of 12t dt, which is 6t squared plus c. So when y equals 5, t equals 1, that implies 5 is equal to 6 plus c, which implies that c equals minus 1. Therefore, y equals 6t squared take 1. And we're done. SQA Advanced Higher Mathematics 2024, Paper 2, Question 10. A metal rod is heated such that its volume increases at a constant rate of 12 millimeters cubed per minute. The volume of the rod is modelled throughout the process by V equals 5 pi r cubed, where r is measured in millimeters. Find the rate at which r is increasing when r is 10. Okay, so we want the rate dr by dt in the end, but we know at the moment metal rod is heated so its volume increases at a rate, so dv by dt, we already know, equals 12. And we already know that v equals 5 pi r cubed. So we can work out dv by dr, but we actually want to know dr by dt. But let me do dv by dr because you can do that. dv by dr is equal to 15 pi r squared. And then using the rules, dv by dt equals 12, but dv by dt is dv by dr times, then there we are, dr by dt. So we can rearrange for dr by dt in a moment, but dv by dt is 12. That equals 15 pi r squared times dr by dt. In other words, dr by dt is 12 over 15 pi r squared. So we have to do that at r equals 10. So when r equals 10, dr by dt is 12 over 15 pi times 10 squared. That equals 12 over 10 times 100. 100 times 15 is 1500. 1500 pi. You can simplify that if you want. 12 into 12 goes 1. 12 into 15 goes 1. 12 2s are 24. 12 5s are 60. 1 over 125 pi in the units are millimeters per minute. So it would be millimeters per minute. Or you can put that all in a calculator and you get about 0.0025 millimeters per min. And you probably would have done that, so I'll put that there for reference. Advanced Higher Maths 2023, Paper 2, Question 11. On a bone set, water stored in a container. The container is a cone with a diameter of 180 at its widest point and a height of 150. The cross section shown. Show that when the level is at a height of h, the volume in the can be expressed by 3 pi h cubed over 24. It even goes and tells us the volume of a cone, in case you forgot, which is 1/3 pi r squared h. So let's start from that position. V equals 1/3 pi r squared h, and it wants us to eliminate r, I suppose. So let's have a look at our triangle. We've got 180 by 150. So if I draw the triangle in terms of there's the height here, and that is 150, and the radius here must be 90, then the ratio between the radius and the height is equal to 90 over 150. So we can use that fact to eliminate our r from our equation, because 150r must equal 90 times h, or in other words, r is 90h over 150, which you can simplify to 9h over 15, which dividing through by 3 gives me 3h over 5. So r is 3h over 5, there's your key fact. So subbing that into this, v must be 1/3 pi times 3h over 5 squared times the height. Let's just keep that separate. So v equals 1/3 pi times 3 3s are 9, so 9h squared times h still over 25. So v equals, tidying that up, That gives us v equals 9 pi h cubed over 3 25s is 75, dividing through by 3, v equals 3 pi h cubed over 25 as required. Part B says, find the rate at which the height is increasing when the height h is 1, 2, 5. Find the rate, so we're differentiating to find the rate of change. So for part B, we're starting off with our equation here, and we can differentiate it with respect to h. So dv by dh is equal to, well, it's 3 3s are 9, so 9 pi h squared over 25. To find the rate at which the height is increasing when h is 1, 2, 5. So we want dh by dt. We've got dv by dh, but we can also work out dv by dt because it says water is pumped into a container at a constant rate of 10 litres per second. So the rate at which the volume is changing with respect to time is 10 litres per second. 10 litres per second, which we can change to standard units because that is 10,000 centimetres cubed per second. And we want to find the rate at which the height is increasing. So the rate for the height, dh by dt, well, that's just going to be dh by dv times dv by dt. dh by dv is 25 over 9 pi h squared, and dv by dt we've just worked out is 10,000. Tidying that up, that gives us 25,000 divided by 9 pi h squared. We could continue to mess about making this nicer, but we've got a number to sub in anyway, so we might as well go ahead and sub it in. It says h is 125, so when h is 125, our rate dh by dt is just going to be 25,000 divided by 9 pi times 125 squared. So 25,000 divided by 9 times pi times 125 squared is 0.056588. Let's just write some of that down. 0.0565 blah blah blah, or 0.057 centimeters per second. And we're done there. SQA Advanced Higher Mathematics 2024 paper 1 question 8. Use the substitution use tan 2x to evaluate this integral. Okay, let's start with u equals tan 2x then. So we're going to have to get rid of the dx anyway. So even if you don't know what to do, you should just start with that. du by dx. Well, sec squared 2x. Start of the exam paper if you don't know, times it by 2 because of a chain. So that means that dx times that is du. So dx is du over that 2 sec squared 2x. Now you might not be able to see what's going on, so just sub it in and see what happens. So let's have a look. Root tan 2x, well, u is tan 2x, so that's the root u I've got. And then we've got cos squared 2x on the bottom. I don't know what the hell that is, so let's just leave it where it is. And I'm timesing that by du over 2 sec squared 2x. Well, that's root u over cos squared 2x times du over 2 times, well, sec is 1 over cos, third letter, helps to remember that. So 1 over cos squared 2x. Well, that's handy because we just cancel each other out. So that gives me root u du over 2. So now we can do our limits. So we've got 0 and pi over 8. So when x equals 0, u equals tan of 0. And the tan of 0 is 0. And when x equals pi over 8, u equals tan, it was 2x, I think. So 2 pi over 8, which is pi over 4. Pi over 4 is 45 degrees. The tan of 45 is 1. So that means our integral just becomes the integral between 0 and 1 of root u du over 2. So that's a half of the integral between 0 and 1 of u to the half du. So what does that give me? That gives me a half, add 1 to the power, divide by the new power, 3 halves becomes 2 thirds. And that's between 0 and 1. So subbing in our numbers, that's a half, 2 thirds times 1 to the 3 halves, minus 2 thirds times 0 to the 3 halves. That's just a half times 2 thirds then, because 1 to the power of anything's 1, and then I've got 0. That's just 2 over 6, which is 1 over 3. And we're done there. SQA Advanced Higher Maths 2023, Paper 2, Question 2. Integrate x squared over x cubed plus 10 dx. So in this case, we can let u equal x cubed plus 10. And then we can find du by dx. So du by dx is equal to 3x squared, which means that 3x squared dx is equal to du, or in other words, x squared dx is du over 3. And we can substitute in now. So our integral of x squared over x cubed plus 10 dx equals the integral of, well, x squared dx is du over 3, so du over 3, and x cubed plus 10 is just u. Well, that's easy, that's just a log. So that integral becomes a third of the log of u plus some constant c, but u, remember, was x cubed plus 10, so that means we've got a third of the log of x cubed plus 10 plus c. Notice the bars round about the log there because it can only be defined for positive numbers, so it's a modulus of SQA Advanced Higher Maths 2023, Paper 1, Question 4. Use integration by parts to obtain x to the 4 log x. So we'll call this one v dash and this one u. So that means v is a fifth of x to the 5 and u dash is equal to 1 over x. So our integral becomes uv, remember, minus the integral of vu dash. So uv is log x times 1/5 x to the 5 minus the integral of v, which is again 1/5 x to the 5, and you've got u dash, which is 1 over x dx. So that gives you x to the 5 log x times a fifth minus a fifth of x to the 5 over x is just x, so the integral of x to the 4 dx. So that gives you a fifth x to the 5 log x minus a fifth times, well, it'll be a fifth of x to the 5 plus c. Got a common factor of 1/25 x to the 5. Then for the first term, we'll need to have 5 log x, because 5 over 25 is a fifth. And then that will just be minus 1 plus c. And we're done there. Question 4. Use integration by parts to find the integral of x plus 2 to x plus 7 to the half dx. So let's make our u equal to x plus 2. Obviously that implies that our u dash or du is just 1. And then obviously our v dash is 2x plus 7 to the half. So we need to integrate that to find v. So that means that v equals, add 1 to the power, divide by the new power, times the differentiation of 2x plus 7, which is 2. That implies that v is simply 1/3. 2x plus 7 to the 3 over 2. So remember, integration by parts means that our integral, u times v minus integral of vu dash. Integral equals u times v x plus 2 times 1/3 of 2x plus 7 to the 3/2 minus the integral of v, which is again 1/3 2x plus 7 to the 3/2, and we're timesing that by du, which is 1, so then that's just that. So we need to integrate 1/3 2x plus 7 to the 3/2. So as an aside, the integral of 1/3 2x plus 7 to the 3/2 dx equals 1/3, add 1 to the power, divide by the new power, times 2, 1/3 times, that'll be 1/5, 2x plus 7 to the 5/2, which is a 15th, times 2x plus 7 to the 5/2. So our integral equals 1/3 x plus 2, 2x plus 7 to the 3/2, minus the answer we just worked out, plus c. So we've got 5x plus 2, 2x plus 7 to the 3/2, minus 2x plus 7 to the 5/2, plus c, and that would be over 15. We can take out a common factor of 2x plus 7 to the 3/2 here. So we've got 2x plus 7 to the 3/2, 5x plus 2, minus, well, we've got 3/2, so I'm going to just have 2x plus 7 to the 1. And you've got plus c, and remember that's all over 15. So that gives us 2x plus 7 to the 3 over 2 times, let's just do this quickly, 5x minus 2x, so we've got 3x, and we've got 10 minus 7 is 3 plus 3 plus c over 15. 3 is a common factor here, so we can say that that is 3 times 2x plus 7 to the 3 over 2, x plus 1 over 15 plus c. Therefore, integral equals 2x plus 7 to the 3/2 times x plus 1 over 5 plus c. And we're done.
SQA Advanced Higher Maths 2024, Paper 2, Question 15. A storage tank contains a mixture of salt and water. An additional amount of salt and water pours in while at the same time some of the existing mixture pours out. The process can be modelled by this first order separable differential equation where W can't be less than 36. W is the amount of salt in kilograms at time t minutes. Initially the storage tank contains 8 kilos of salt. Express W in terms of t. Okay, part A. So I've got dW, 120 of that, equals 36 minus W times dt. So in other words, dW over 36 minus W equals dt over 120. Integrate both sides in. That's a log for this one, so it's the log of 36 minus W, but chain rule, remember, applies, so times minus 1. That equals, well, that's just 1 over 120, and we've got t, so it's t over 120 plus some constant, let's call that c. And therefore w equals minus e to the minus t over 120 plus d plus 36. So now we can separate our variables out, minus e to the minus t over 120 times e to the d plus 36. We'll just say that let a equal e to the d. So w equals minus a e to the minus t over 120 plus 36. I mean, initial conditions were that when t equals 0, w equals 8. So that means that 8 equals minus a plus 36. So a must equal 36 minus 8, 26, 27, 28. And therefore w equals minus 28 e to the minus t over 120 plus 36. And we're done there. Part B, find the rate at which the amount of salt is increasing after 67 minutes. So we want to know what the w by dt is at t equals 67. Two ways to do this. If you go back to your initial equation, and since you've already got w here, you could sub 67 in to get w, and then sub w in to get into dw by dt. That's one way, or a better way. Let's just work out dw in terms of t, dw by dt, using this formula. So we've got e to the minus t over 120. So that's still e to the minus t over 120. We've got minus 28, but that's going to be times by the derivative of t over 120 minus, which is just 1 over 120. So you'll get 28 over 120. And then you've still got plus 36, but that's gone. So at t equal to 67, dw by dt is 28 over 120 e to the minus 67 over 120. Doing that in a calculator then, e to the power of minus 67 over 120 is that, times 28 over 120 is 0.134. And the rate would be kilograms per minute. So we're done there. Part C. As the process continues, the amount of salt approaches a limit, L kilograms. Find the value of L. So W equals minus 28 e to the minus t over 120 plus 36. So we're wanting to know what happens as t goes to infinity. Well, w goes to minus 28 e to the minus infinity over 120, which is still minus infinity, plus 36. So we need to know what happens to e as it approaches negative infinity. Well, there's the graph of e. As that gets smaller and smaller, it gets closer and closer to 0. So we can say that w approaches 0 plus 36. So w approaches 36, which means our limit L is equal to 36 kilograms. And we're done there.
SQA Advanced Higher Mathematics 2023, Paper 2, Question 13. Pupils scored in the long jump element of a decathlon can be calculated using the solution to a differential equation. M minus 220 dp by dm equals 1.4p, where m is greater than 220. M is the distance jumped in centimetres, p is the points scored. And then it gives you some information. A jump of 807 centimetres scores 1079 points. Find an expression for p in terms of m. So if we separate the variables to p on one side and m on the other, we can probably integrate both sides. So let's just start working on that. So we've got m minus 220 dp by dm equals 1.4p. So if I can divide the left by 1.4, so that will give me the p over 1.4p. And the right hand side, I'll take the dm up, so I'll have dm, I'll divide by m minus 220. So I've now just separated it out so I can integrate both sides. So that means I've got the integral of the p over 1.4p equals the integral of dm over m minus 220. Well, they're just logs, aren't they? So that implies that I've got 1 over 1.4 times the integral of the p over p, can you just take 1.4 out, equals the integral of the m over m minus 220. So what's that going to give me? Well, it's going to give me 1 over 1.4 times log, as a p, equals the log of m minus 220. So I can take the 1.4 over the other side, log p equals 1.4 log, that's plus c of course, m minus 220, and take the 1.4 up as a power. So we get log p equals log of m minus 220 to the power of 1.4 plus c. Now, c could be anything, so we could just save it. To eliminate that c, we can just times it by log e, because log e is 1. So we could just save it. We've got log p equals log of m minus 220 to the power of 1.4 plus log base e to the power of c times that, or to the power of c if I put it back up. So that'll be c times, c is just your number, times 1. So now we can add these logs together. So log p becomes, using the rules of logs, add means I can times, so it's just m minus 220 to 1.4 times e to the c for 1 log. In other words, e to the power of c, m minus 220 to the power of 1.4. And now we can eliminate the logs for both sides to save it p is equal to e to the power of c, m minus 220 to the power of 1.4. So now using information in the question, when m is 807, that's the distance, p is 1079. So when m is equal to 807, p is equal to 1079. So we're going to sub that in. So 1079 equals e to the power of c times 807 minus 220 to the 1.4. So that means e to the c must be 1079, over 807 minus 220 to the 1.4. 1079 divided by 807 minus 220 to the 1.4 is 0.1435. So that means we can just say that p is equal to 0.144 times m minus 220 to the power of 1.4. And we're done there. Question 8, differentiate egg log x minus x with respect to the x, and then part B, find the general solution to this differential equation. So part A, let's say y equals x log x minus x, and we're going to use the product rule on x log x. So we've got u is equal to x, we've got u dash is 1, and then v is log x, of course, which means v dash is 1 over x. And just a reminder, so we've got u dash v plus v dash u. So that's 1 times log x plus 1 over x times x, or log x plus 1. So that means that on this side, differentiating it, the y by dx must be log x plus 1 minus 1, because differentiating of x is just 1. So the y by dx in this case is just log x. Part B, hence find the general solution to this differential equation. The y by dx plus y log x equals x to the power of minus x. So our integrating factor from part 1 is simply going to be e to the power of the integral of log x dx, and we know then that is just going to be e to the x log x minus x. So that means our integrating factor is e to the log of x to the power of x times e to the minus x. So that means our integrating factor is just simply x to the power x times e to the minus x. So we can just times both sides by our integrating factor. So we've got x to the power x e to the minus x dy by dx plus y x to the power x e to the minus x log x, and that equals the right hand side, which is x to the power minus x times x to the power x e to the minus x. So that implies we've got d by dx of x to the power x e to the minus x times y equals e to the power minus x. So x to the power minus x e to the minus x y must equal the integral of e to the power minus x dx. So x to the power x e to the minus x y equals minus e to the minus x plus c. And therefore y is just minus e to the minus x plus c over x to the power x e to the minus x. And that final answer can be left in a lot of different ways.
SQA Advanced Higher Mathematics 2024, paper 2, question 13. Quite a long one this. Express minus 2 over x plus 1 in partial fractions. So that's okay to start with. Minus 2 over x plus 1 just equals a over x plus b over x plus 1. So that means that ax plus 1 and bx equals negative 2. So when x equals 0, we get 0 plus 1 is 1, a equals minus 2. And then when x equals minus 1, that's 0, we get minus b equals minus 2. So b is equal to 2. So our partial fractions are a, which is minus 2, over x, plus b, which is 2 over x plus 1, or if you prefer, 2 over x plus 1 minus 2 over x, if you like the look of that better. Part B, use integration by parts to find the integral of x e to the 3x dx. So the integral of x e to the 3x dx, so we've got uv dash. So the one we want to disappear is x when we do u dash, so that's u and that's v dash. So that means that u dash is equal to 1 and v is the integral of e to the 3x, which is a third e to the 3x. And just a reminder of your formula, the integral of uv dash equals uv minus the integral of vu dash. So that gives us uv dash is uv, so x times a third, so a third x e to the 3x minus the integral of vu dash, well v is a third, so I'll take the third out, times the integral of e to the 3x, and u dash is 1. So you get it simplified to there quite quick. So that gives me a third x e to the 3x minus, we already know e to the 3x goes to a third e to the 3x, so that's going to be a ninth e to the 3x, and make sure you add a c. How simple you want to go with this is up to you. A nice thing to do, which I noticed someone else doing, was taking a ninth e to the 3x out instead of just a third. If you take a ninth out, you get a nice thing because you get 3 here times x, because 3 over 9 is a third, and then that only gives you 1, so minus 1 in the bracket plus c. So that's a nice way to leave it. Using your answers to A and B, solve this differential equation. Okay, so we've got a differential equation. I've written this here, and that is of the form dy by dx plus p of xy equals q of x. We wouldn't ask the q of x, but it does equal q of x. So our p of x in this case is minus 2 over x plus 1, which is handy because that was part A. And our q of x is x cubed e to the 3x over x plus 1 squared. Okay, so let's go for there. If you recall, a quick method for this is that either the integrating factor times y equals the integral of the integrating factor times q of x dx. And so the problem I've got is I need to find my integrating factor. So my integrating factor, I of x, is e to the integral of p of x dx. So what is p of x? P of x is this, and the integral of p of x, well, we did that up here. Well, we've not, but we've expressed it in partial. This thing was expressed in partial fractions, so we can just write down 2 over x plus 1 minus 2 over x. So let's just do that here. The integral of p of x equals the integral of 2 over x plus 1 minus 2 over x dx. Well, that's just 2 log x plus 1 minus 2 log x. Well, that's just log x plus 1 squared over x. That integrating factor is equal to e to the power of a log x plus 1 squared over x squared. E to the power of a log is just taking away the log, so you get x plus 1 squared over x squared. So there's our integrating factor. So now we can just write our integrating factor times y equals the integral of x plus 1 squared over x squared times x cubed e to the 3x, x cubed e to the 3x over x plus 1 squared. Try and cancel anything we can. So we've got x cubed and x squared. So I can do that and get x to the 1 and do that. You've got x plus 1 squared and x plus 1 squared, so you can just say goodbye to them. So that equals the integral of x e to the 3x. This should have a dx on it. So x plus 1 squared over x squared times y equals that. 1/9 e to the 3x, 3x minus 1 plus c. Make sure you get a plus c in there. So that equals that. So now we can rearrange for y. So y equals, dividing through by a fraction just times by the reciprocal, so I'll put the x squared on the top. So we've got x squared e to the 3x, 3x minus 1 over 9 x plus 1 squared. And then make sure that c becomes something as well, cx squared over x plus 1 squared. Make sure you do that for the c or you'll lose a mark. Would we want to simplify that? I don't think I can. That's factorised, that's factorised, that's factorised, that's factorised, nothing common to that. That's factorised. You know, I think I'd leave that there and say I'm done there. SQA Advanced Higher Mathematics 2024, Paper 2, Question 4. Solve this differential equation. So it's a second order. D squared y minus 2 minus 8y is 0. So yep, and we can just use the auxiliary equation then. And we're given some information, but let's just start there. M squared minus 2m minus 8 is 0. Quick factorisation on that to give us m and m. 4 and 2 minus 4 plus 2. So m is minus 2 and m is 4. So that means that our general solution is y equals a e to the, we'll just put the positive one first, 4x, plus b e to the minus 2x. Doesn't really matter the order you put them in. But then we can find our particular integral by substituting in our initial conditions. So when y equals minus 2, x is 0. So that gives us minus 2. E to the power of 0 is 1, so that's a plus b. And then differentiating it, the y by dx is equal to 4a e to the 4x minus 2b e to the minus 2x So it says 22. So 22 equals 4a minus 2b. So you've got two equations. Let's just solve them simultaneously. I'll put them one above the other. So I'll just times the top one by 2. So that's going to give me 2a, 2b minus 4, 4a minus 2b, 22. Adding them together, you get 6a is equal to 18. So a equals 3. And that implies that b must equal minus 2 minus 3 is minus 5. So we get 3 and minus 5. Now to get our answer then, y just equals, remember it was a to the 4x plus b to the minus 2x, 3e to the 4x plus b minus 5e to the minus 2x. That's our particular integral, and we're done there. SQA Advanced Higher Maths 2023, Paper 1, Question 5. Find the particular solution of this differential equation. So let's set up our m squared minus m, m squared minus 4m minus 5 equals 0. And that gives us m and m. It gives us 5 and 1. Minus 5 plus 1 equals 0. So x equals minus 1 or x equals 5. So for our general solution, we know it's going to be in the form of, well, this is two distinct roots. So you're going to have y equals a e to the minus x plus b e to the 5x. So now let's work on our right hand side. We have got 10x squared plus 11x minus 23. Looking at our right hand side, since we've got 10x squared plus 11x minus 23, the form is going to be y equals ax squared plus bx plus c. So now we can differentiate that twice to find dy by dx and d2y by dx squared. The y by dx is just going to be 2ax plus b, and d2y by dx squared is simply going to be 2a. So now we can sub that back into the original equation. So the original equation was d2y by dx squared minus 4 dy by dx minus 5y equals 10x squared plus 11x minus 23. So d2y by dx squared is 2a minus 4 times 2ax plus b, and then we've got minus 5 times ax squared plus bx plus c, and that equals our right hand side, but let's just tidy that up. That gives us 2a minus 4 2s are 8ax minus 4b minus 5ax squared minus 5bx minus 5c. Putting it all in the right order, you'll have minus 5ax squared. That's that one done. Then minus 8ax minus 5bx. That's that one done and that one done. Plus 2a minus 4b minus 5c. And we're going to equate that to 10x squared plus 11x minus 23. So equating the left and the right hand side, that implies that minus 5a is equal to 10, so a is equal to minus 2. In our x terms, we have got minus 8a minus 5b equals 11. Minus 8 times minus 2 is 16, minus 5b is 11, so minus 5b is minus 5, so b is equal to 1. Now looking at our constant terms, we have got 2a minus 4b minus 5c is equal to minus 23. 2a is minus 4. 4b is also minus 4. Minus 5c is minus 23. So you get minus 8 minus 5c is minus 23. Minus 23 plus 8 is minus 15. So minus 5c equals minus 15. And therefore c is equal to 3. So now we know that our y must equal a e to the minus x
plus b e to the 5x minus 2x squared plus x plus 3. So now we can differentiate that, because we also know from the start of the question, way back up here, that when y is 2, dy by dx is 14 when x is 0. So finding our dy by dx first, that's minus a e to the minus x plus 5b e to the 5x minus 4x plus 1. So when y equals 2, we get 2 equals a plus b, and then 0, 0 plus 3. Or to put it a better way, a plus b equals minus 1. And then when dy by dx equals 14, we get 14 equals minus a plus 5b plus 1. Or minus a plus 5b equals 13. So we've got two equations to solve simultaneously. I'll just write them one above the other. 5b plus b is 6b. 13 minus 1 is 12, so b is equal to 2. And then subbing that into a plus b equals minus 1. You've got a plus 2 equals minus 1, so a equals minus 3. So then we can just now write our final solution, y equals minus 3 e to the minus x plus 2 e to the 5x minus 2x squared plus x plus 3. And finally, we're done there. Question 13, the last one. A secure spotlight is situated 10 metres from a fence, straight fence. Spotlight rotates at a constant speed, makes a full revolution every 12 seconds. And the situation at time second, t seconds is modelled on the diagram below. L is your position of your spotlight. G is the point nearest to the fence on the spotlight. P is the position where the light hits the fence. Theta is the angle between these two positions, and x is the distance in meters from G to P, as shown. And we've got quite a big question to go through. The first one says, show that the theta by dt equals pi over 6 radians per second, and then dx by dt is 5 pi over 3 sec squared theta meters per second. We're then going on to prove an identity, and then find the exact value of dx by dt. So let's go straight into question A. So for question A, I've copied and pasted the relevant bits, the information, the diagram itself, and the fact that we've got one full revolution every 12 seconds. So for part A, we've got one full revolution, so 2 pi radians every 12 seconds. So 2 pi radians in 12 seconds means you've got 2 pi over 12 radians in 1 second. Simplifying that gives us pi over 6 radians. And therefore, the theta by dt is simply pi over 6. Nice and simple there. B, show that dx by dt is 5 pi over 3 sec squared theta meters per second. So if you look at our diagram, we've got a right angled triangle, so it's just SOHCAHTOA. So if you look, we've got opposite is x and adjacent is 10. So the tan of our angle is simply x over 10. That implies that x equals 10 tan theta. dx by d theta must equal 10 sec squared theta. Tan goes to sec squared theta. Dx by dt then is what we're trying to work out. So dx by dt will be dx by d theta times d theta by dt. That's 10 sec squared theta times pi over 6. That's part A, remember. We worked that out. So dx by dt, 10 pi sec squared theta over 6, which is 5 pi sec squared theta over 3. So dx by dt is 5 over 3 pi sec squared theta meters per second is proved. Okay, we'll do a trig identity to prove that 1 plus tan squared theta is sec squared theta. So let's just start with the left hand side, 1 plus tan squared theta. Well, that's 1 plus sine squared theta over cos squared theta. Well, that's just 1 plus 1 becomes cos squared over cos squared. Plus sine squared over cos squared. That equals cos squared plus sine squared over cos squared. Cos and sine is 1, so it's 1 over cos squared theta, which is equal to sec squared theta. And therefore we've proved that 1 plus tan squared theta equals sec squared theta. Part C says, hence or otherwise find the exact value of dx by dt when p is 5 meters from G. So recall dx by dt we've already worked out, and we've already been told in the question actually is 5 over 3 pi sec squared theta. But from the previous part, we know that sec squared theta is 1 plus tan squared theta. So dx by dt is 5 over 3 pi 1 plus tan squared theta. So from A, x is 10 tan theta. So when x equals 5, we get 5 equals 10 tan theta, which implies that tan theta equals a half, or 5 over 10. So we can substitute a half in for tan squared theta. So dx by dt is going to equal 5 over 3 pi 1 plus a half squared. Obviously at x equal to 5. So that equals 5 over 3 pi one plus a quarter, which is 5 over 3 pi, and 5 times 5 quarters. So that equals 25 pi over 12. So dx by dt equals 25 over 12 pi meters per second for our units. And we're done.
SQA Advanced Higher Maths 2024, Paper 2, Question 8. A solid is formed by rotating part of a curve with equation y equals 1 over the square root of 1 plus x squared about the x-axis through 2 pi radians from 0 to x equals a. And the value of the volume is pi squared over 3. Find a. So the volume is v equals the integral of pi times y squared dx. And we have got between 0 and a. And that equals, just to remind us, pi squared over 3. So as long as you know that, this question should be reasonably straightforward. So that's pi times, well, if you the integral of 0 to a, y squared, let's have a look, 1 over square root of 1 plus x squared dx equals pi squared over 3. So check that example for that one. I think that's the inverse tan. So that becomes pi times the inverse tan of x between 0 and a equals pi squared over 3. So that's pi times the inverse tan of a minus the inverse tan of 0 equals pi squared over 3. So you can eliminate a pi for both sides then, and the inverse tan of a we get on this side minus the inverse tan of 0 is 0. That's not times by pi anymore because I'm just going to say that's pi over 3, just to eliminate a pi for both sides. So that means the inverse tan of a is pi over 3. So that means that I can just kind of work that out. If I draw an exact value triangle, I'm just going to think in degrees and then change it back. 2, 1, root 3. If the inverse tan of a is pi over 3, that means a must have been 60 root 3. And we're done there.
Question 7. Use the substitution u equals y squared plus 1 or otherwise to find the exact value of the integral between 0 and 5 of 4y over the square root of y squared plus 1. So if u equals y squared plus 1, then du by dy must equal 2y. So that implies that du equals 2y dy. So 2 du must be 4y dy. So make our limits for the integral. So remember, at y equal to 0, u equals 1, and at y equal to 5, u equals 5 squared plus 1, which is 26. The integral between 1 and 26 of 2 du over the square root of u. That's the integral between 1 and 26 of 2u to the minus a half du. So add 1 to the power and divide by the new power, u to the half. 2 divided by a half is 4. We can put our limits in. So we've got 4 times root 26 minus 4 times root 1, which is equal to 4 root 26, and root 1 is 1, so minus 4. Okay, 7b. Student engineers are using a 3D printer to make a model, and it says, relative to a suitable set of axes, the cross-section is symmetrical about the y-axis and is represented in the first quadrant by the equation we just started off with, between 0 and 5 on the y-axis. State the area of the cross-section. We've just worked out that the definite integral between 0 and 5 and the y-axis is this. So for part B, we've got this picture. Symmetrical about the y-axis, so on the other side it goes along and does the same thing. So you've just got another one of these and another one of these. So it's going to be 2 times 4 root 26 minus 4, 8 root 26 minus 8 units squared, because it's area. Question C says express y squared over y squared plus 1 in the form a plus b y squared plus 1, where a and b are real numbers. If it says the curve is rotated through 2 pi radians about the y-axis, find the volume. So we've got y squared divided by y squared plus 1. So that's y squared, no y, and no number. The y squared goes into y squared one time. 1 times y squared plus 1. 1 times 1, take away. We get nothing, plus nothing, minus 1. And therefore, a equals 1, b equals minus 1. We've got 1 minus 1 over y squared plus 1. So the curve x equals 4y over the square root of y squared plus 1 between 0 and 5 will be rotated through 2 pi radians about the y-axis to make the model. Find the volume of the model. So just a reminder, this is testing if you know that the volume equals pi times the integral of x squared dy. So let's work out our x squared. X squared just equals 4y squared is 16y squared over y squared plus 1. So our volume is equal to pi times the integral between 0 and 5 of 16y squared plus y squared plus 1 dy. The volume is 16 pi, the integral is 0 and 5 y squared over y squared plus 1 dy. That's 16 pi, the integral between 0 and 5 of 1 minus 1 over y squared plus 1 dy. So we can now directly integrate it. We've got 16 pi, 1 becomes y, and if you look at the start of the exam paper, that's the inverse tan. So it's the inverse tan of y. Between 0 and 5. So substituting 5 in, we get 16 pi, 5 minus inverse tan of 5. Take away 0, the inverse tan is 0. That gives us 16 pi, 5 minus inverse tan of 5. 5 16s is 80, so we get 80 pi minus 16 pi, the inverse tan of 5, units cubed, because it's volume. And we're done.
SQA Advanced Higher Maths 2024, Paper 2, Question 3. Use Gaussian Elimination to express z in terms of lambda for a system of equations. Find lambda for when it's inconsistent, and then determine the solution of the system when lambda is -1. So Gaussian Elimination, I've got 1 minus 1 minus 3 equals 1. 2 minus 3 minus 5 is 8. And 1, 2, lambda is -7. I'll usually put a wee dotted line on there. So there is my matrix, and what I've done is I've said that row 2 is going to become row 2 minus 2 row 1, and simultaneously I'm going to have row 3 becoming row 3 minus row 1, just to get my zeros in the left hand side. So we've got 1 minus 1 minus 3 and 1, and then you've got 2 minus 2 is 0, minus 3 plus 2 is -1, minus 5 plus 6 is 1, and 8 minus 2 is 6. And then 1 minus 1 is 0, 2 plus 1 is 3, lambda plus 3, and finally -7 minus 2 is -9, -7 minus 1 is -8. Don't know why I said -2. Okay, so now we want a 0 on the bottom line, so we're going to go row 3 equals row 3 plus 3 row 2. So we've got 1 minus 1 minus 3, 1, 0 minus 1, 1 and 6, 0, 0, lambda plus 3 plus another 3 is lambda plus 6, and -8 plus 3 sixes is 18, gives you 10. So that means that this number times z is usually equal to 10. So we could say that lambda plus 6 times z equals 10. In other words, z is 10 over lambda plus 6. And we're done there for part A. Part B, state the value of lambda for which the system's inconsistent. Inconsistent. No work required for this when lambda equals -6, because you can't divide by a 0. Determine the solution of this system when lambda is -1. Okay, so we've got a bunch of equations. So lambda's -1, and we've got z equals 10 over lambda plus 6. That's 10 over -1 plus 6. That's 10 over 5, which is 2. So we know that z equals 2 is our first solution. Next equation, -1 minus 1 plus z is 6. So -1 plus 2. Next equation, minus y plus z equals 6. Minus y plus z equals 6. So that's minus y plus 2 equals 6. So minus y is 4. In other words, y is -4. And there's our y. Then the last equation, x minus y minus 3z is 1. X minus y minus 3z equals 1. So we've got x plus 4, because minus minus. 3 2's is 6, minus 6 equals 1. So x minus 2 is 1, and x must be 3 then. So we've got x, y, z, so we're done there, and I'm happy with that. 3, minus 4, and 2. A system of equations defined as this. Use Gaussian elimination to see if they're redundant, inconsistent, or have a unique solution. So let's set up our Gaussian elimination. We've got 1 minus 3, 1 minus 1, 3 minus 2, 4 and 11, 1, 4, 2 and 15. And remember, the goal here is simply to get zeros in these three places. So the first thing I can do is do row 3 becomes row 3 minus row 1. But simultaneously, I can do row 2 becomes row 2 minus 3 row 1. So being very careful, we get 1 minus 3, 1 minus 1. 3 minus 3 is 0. Minus 2, but then it'll be plus 9 is 7. 4 minus 3 is 1. And 11, and it'll be plus 3 is 14. And then the bottom one, row 3 minus row 1 gives you 0. 4 plus 3 is 7. 2 minus 1 is 1. 15 plus 1 is 16. Now we can get a 0 in this place by doing this minus this. So row 3 becomes row 3 minus row 2. So we can have 1 minus 3, 1 minus 1, 0, 7, 1 and 14, 0, 7 minus 7, 0, 1 minus 1 is 0, 16 minus 14 is 2. 0x plus 0y plus 0z equals 2. 0z cannot equal 2, so therefore the system is inconsistent.
SQA Advanced Higher Maths 2024, paper 1, question 4. Matrix A has this 6, 1, 11, 3. Find the inverse matrix. Okay, the inverse matrix is equal to 1 over the determinant of A times 6, 3. Change position, 3, 6. And the other ones stay where they are, but I move the sign. So what's the determinant A then? Well, it's 6 times 3. Minus 1 times 11, the diagonals. That's 18 minus 11, which is 7. So that means that the inverse matrix is a 7th of 3 minus 1 minus 11, 6. And we're done there. Part B says, find the matrix M such that AM equals B. There's a couple of ways to do this, but I think the simplest way, especially when we've got the inverse already, is to start with the fact that AM equals B. And we can put an inverse here. And then just put it here. Now make sure you put your orders in the right place. I put it in front, so I put it in front. A inverse A is I, so IM equals A inverse B, but I times M is M. So M is just A inverse B. So A inverse was 1/7. 3 minus 1 minus 11, 6 times B was minus 4, 3 minus 5, 2. Times everything through, we get 1/7. 3 minus 12 plus 5 is minus 7. 3 3's is 9, minus 2 is 7. 40 minus 30, 44 minus 30 is 14, and then minus 33 plus 12 is minus 21. So we'll get minus 7, 7, 14 minus 21. So then we just divide by 7 then to get minus 1, 1, 2 minus 3, and we're done there. SQA Advanced Higher Maths 2023, paper 2, question 3. The matrix A is defined as this matrix, where x is a member of real numbers. Find an expression simplified for the determinant of A for 2 marks, and then determine whether the inverse exists for all values of A. So the determinant of the matrix, let's start with that. So we're going to have 2, and then we delete these rows and columns times the determinant of this matrix. So 2 times minus 1, 0, 0, minus 2. And then it's minus 2x times the determinant of, I'll delete this row and column, x0, 1, minus 2. And then it's plus again the 4 times the determinant of x minus 1, 1, 0. So then we can go ahead and solve that. So that gives us 2 times 2 minus 2x times minus 2x. Plus 4 times, and be careful now, it's just 1 because it's 0 minus minus 1. So that gives us 4 plus 4x squared plus 4, or a nicer way, 4x squared plus 8. And we're done there. Let's move on to part B. Part B, with the determinant for which values of x the inverse matrix exists. So our determinant, remember, is equal to 4x squared plus 8. And for the inverse to exist, the determinant cannot equal 0. So for the inverse to exist, det A cannot equal 0. So we're just looking to see what values of 4x squared plus a can x be so that it's never 0. So we've got 4x squared plus 8. That is never equal to 0. And why is that? Because x squared is always greater than or equal to 0. And that means you could then say that 4x squared is all plus 8 would always greater than or equal to, well, it would be 8. Because you would have, if you square a number, the smallest you can get is 0, plus 8 is 8. And therefore, the inverse exists for all values of x. Advanced Higher Maths 2024, paper 1, question 6. Find the 2x2 matrix A associated with a reflection in the x-axis. So you can draw yourself a picture if you're going to get stuck on this. Imagine a point, x and y. It's getting reflected over the x-axis. X stays the same. We've got minus y. So you can think of this as something times xy equals x minus y. And what's a 2x2 matrix? Well, 1 times x is x. 0 times y is y, so that will give us x, and we want minus y, so we want 0x, and we want minus 1y. So there's our matrix, 1, 0, 0, minus 1, and we're done there. Describe a transformation associated with the matrix 0, 1, 1, 0. So we've got 0, 1, 1, 0 as our starting position, that's getting times by x, y. So we've got 0 times x is 0 plus y, that gives me a y. 1 times x plus 0y gives me an x. So if you can't see it yet, imagine you've got a point along x up y, say x, y, and then y becomes x, so along y up x. If you roughly draw it roughly accurate, you should be able to see you're getting a reflection along y equals x, if you didn't know. So reflection in line y equal to x. Part B, find a 2x2 matrix called C associated with reflection followed by transformation associated with 0, 1, 1, 0. So just remember when you're doing these, you actually work backwards from the finishing point. So I start with 0, 1, 1, 0, and I times by my 1, 0, 0, minus 1, because that's the first thing. So 0 times 1 is 0, 1 times 0 is 0, so that's a 0. 0 times 0, and 1 times minus 1. 1 times 1, and 0 times 0. 1 times 0, and 0 times minus 1. So we get that matrix. It doesn't ask us to say anything about it, so I'm done there. SQA Advanced Higher Maths 2023, Paper 1, Question 9. State the matrix A associated with an anticlockwise rotation of pi2 radians about the origin. So for part A, we just go to the start of our exam paper and sine of theta, with a rotation of theta anticlockwise about the origin is cos theta minus sine theta cos theta. So then we can just say our answer is cos pi over 2 minus sine pi over 2 sine pi over 2 cos pi over 2. So the cos of pi over 2, the cos of 90 is 0. So we get 0. The sine of 90 is 1. So we get minus 1, 1 and 0. And we're done there. The matrix B is given by this matrix. AB is associated with an anticlockwise rotation of alpha radians. Determine AB. So for part B, A times B is equal to 0 minus 1, 1, 0 times our matrix minus root 3 over 2, a half, minus a half, and minus root 3 over 2. Multiplying them together, we've got 0 times that minus 1 times that is a half. 0 times a half is 0, minus 1 times this is root 3 over 2. 1 times minus root 3 over 2 plus 0 is minus root 3 over 2. And 1 times a half is 1, and 0 is a half. So there's AB. It then says, find the value of alpha. Remember, this represents an anticlockwise rotation. So we're looking at cos theta minus sine theta, cos theta again. So for part 2, I know that cos theta must equal a half. The inverse cos of a half is equal to 60 degrees or pi over 3. But is also equal to another answer of 300 degrees, which is 5 pi over 3. So it's one of those two, so then we need to examine another one. So let's examine this one here, sine theta. Sine theta is minus root 3 over 2. The inverse sine of root 3 over 2 is simply pi over 3. So using our cast diagram, sine is negative in this case, so we get pi plus pi over 3 and pi minus pi over 3. So this one again leads to 5 pi over 3. So 5 pi over 3 for that one. Go alpha is equal to 5 pi over 3, and we're done there. Part C, determine the least possible interval of n such that a, b to the n equals I, where I is a 2 by 2 identity matrix. A couple of ways you can do this actually. You could just keep doing it over and over again, but there is a simpler way. If we think of AB as our rotation is 5 pi over 3, we're saying that for part C, AB to the n equals the identity matrix, which means if you think about it going around 5 pi over 3, how many times does it have to go around 5 pi over 3 till it gets back to where it started? So in other words, we're saying that n, some multiple of 5 pi over 3, has to go around to be 2 pi to get back to where it started. So some multiple of 2 pi. And we're just solving for that. So we're looking for the first value of n, which produces a multiple of 2 pi. So if we try 1, we get 5/3 pi. That's not a multiple of 2 pi. Try 2, it's obviously not going to work. 3 is going to give us 5 pi, which isn't 2 pi. 4 or 5 is not going to work. If we try 6, 6 over 3 is 2. 2 5s is 10. 10 pi is a multiple of 2 pi. So n equals 6, and we're done there. This has been Clelland Maths Today. We've looked at the Advanced Higher Maths 2023 Paper 1. Take care, stay safe, and goodbye. SQA Advanced Higher Maths 2024 Paper 1 Question 2. The complex number is defined as z equals 1 plus I, express it in polar form. So to do polar form for part A, I want the size of Z. Well, that's just the square root of 1 squared, and it's 1I plus 1 squared. 1 plus 1 is 2, so that's root 2. And then we want to find tan theta, because remember, if you think of this on a diagram, you've got 1, 1 here, and you can imagine there's your theta there. So it goes along 1 and up 1. So that means that tan theta equals 1. And that means that theta is the inverse tan of 1, which is pi over 4, 45 degrees. Because it's an exact value. So now we can just express it in the correct form. Z equals root 2. And then you've got cos theta, which is pi over 4, plus I sine theta, which is pi over 4. And just check on the principal argument. You probably don't need to be, but remember that's between minus pi and pi. So yeah, we are. So we're done there. Part B says, use the Moivres theorem to do ZA. And it says evaluate it, so work it out. So ZA is root 2 to the power of 8, cos 8 pi over 4, plus I sine 8 pi over 4. Simplifying that out, well, root 2 times root 2 to the power of 8, or root 2 times root 2 is 2. So that's the same as 2 to the power of 4. Cos 8 divided by 4 is 2 pi, plus I sine 2 pi. Now, if you're leaving it in this form, you would actually put it back in the principal argument, but actually have to evaluate it. So we might as well just go ahead and evaluate it. 2 times is 4 times 2 is 8 times 2 is 16. The cos of 2 pi, well, 2 pi is 360 degrees. That is equal to the cos of 0 as well, which is 1. So that's just 1. And the sine of 360, well, 360, that gives me 0. So plus 0. 16 times 1 plus 0 is 16. And we're done there.
Advanced Higher Maths 2023, Paper 1, Question 6. Express Z equals 1 plus root 3I in polar form. Quite standard stuff, this. We need the modulus of Z, which is a bit like Pythagoras, I suppose. You've got 1 squared plus root 3 squared, square rooted. That's 1 plus 3. I'll just go straight to 2, shall we? And we're done there. And then we need the argument of Z. So that's going to be the inverse tan of root 3i, so root 3 over 1. Non-calculator paper, you should just know the inverse tan of root 3 is 60 degrees. Which is pi over 3. Means that Z equals 2 times the cos of pi over 3 plus I sine pi over 3. And we're done there. Part B, hence or otherwise show that Z cubed is real. So Z cubed, we can use the Moivres theorem for this. That's going to be 2 cubed times the cos of 3 pi over 3 plus I sine 3 pi over 3. Well, 2 cubed is 8. Cos of 3 pi over 3 is just the cos of pi plus the I sine the pi. And you should know what the cos of pi and the I sine the pi is. The cos of pi minus 1. And the sine of pi is 0. So that gives us 8 times minus 1, which is minus 8, which is a member of the real numbers. Therefore, Z cubed is a member of the real numbers. And we're done there. Complex numbers, SQA Advanced Higher Maths, 2019, Spec Paper 2, Question 7. It says Z is root 3 minus I. Plot Z on an Argand diagram. So part A, we want an Argand diagram. Quite simple, this really. We're just going to be plotting a coordinate here. So it's really testing if you know what an Argand diagram is. There's an imaginary axis and there's a real axis. And we've got root 3 is the real part and minus I, or minus 1, then minus 1i is the imaginary part. So we're just literally saying I've got a coordinate down here somewhere, which is root 3 along and minus 1 down. So there we are. That's it, plotted on our Gantt diagram. Sometimes people connect it up to the origin, which is completely fine, but a point is all you need, and you can literally put root 3 on the real part and minus 1 on the imaginary part and kind of show that that is in there. Okay, part B, let W equal AZ, A is greater than 0, express W in polar form. So W equals AZ. So let's just write out what that is. You're going to have A root 3 minus AI, I suppose, and we want that in polar form, so we need the modulus in the argument. So the modulus is the size of omega, so that is just like Pythagoras, the real part squared plus the imaginary part squared. So you've got square root of A root 3 all squared plus minus A squared. Root 3 squared is just 3, so that's the square root of 3A squared plus A squared. That's square root of 4A squared, so that is just 2A. And then our argument is tan theta, so tan theta in this case, the imaginary part is minus A, over the real part is A root 3. That simplifies to minus 1 over root 3. Now, I've already drawn it on our Gantt diagram. I would have done it at this point anyway to check which quadrant we're in. We now know we're in 1, 2, 3, 4th quadrant. So this is a paper 2, but it could have been an exact value, this, I suppose. So, because 1 over root 3, if you think of this as being 60, which is pi over 3, and pi over 6, and then you've got 1, 2, root 3, then pi over 6 is 1 over root 3. So we need to see then what our argument is going to be. So a cast diagram, since we know we're in here, it's 2 pi minus pi over 6. So our theta is that. 2 pi, well, that's 12 pi over 6 minus pi over 6, which is 11 pi over 6. Now, I usually leave it in the principal argument. You don't necessarily have to unless it says so, but I will do for this case. So our principal argument is, remember, that is between minus pi and pi. So since that's above pi, I can just take away 2 pi basically. 11 pi over 6 minus 2 pi. Well, 2 pi is 12 pi over 6. So that's going to give me in the principal argument minus pi over 6, which is a lot nicer. So now in polar form, W is just equal to 2A cos theta plus I sine theta. Cos minus pi over 6 plus I sine minus pi over 6 as well. And we could just leave it like that. I mean, you could get rid of the minus pi's over 6's to make it a minus in the middle instead, but that is completely fine. So I'm just going to stop there. Question C, express W8 in the form K an x I root y. Okay, let's copy this down. So this is the Moivres theorem really, but then working backwards from there, there's other ways to do it. You could start with a W and do squared and then power 4 and power 8, but let's might as well do the Moivres theorem. W8 is equal to, well, it's just this bit to the power of 8, and then you just times the angles by 8, so minus 8 pi over 6 plus I sine minus 8 pi over 6. So that's what we need to work out. But we have got a calculator, but I'm just going to simplify it anyway. So 2 to the power 8, well, that is 2 2s is 4 times 2 is 8, 16, 32 is 64, 128, 256, I think. So that's 256 to 8 to the A to the 8. And then I've got cos, well, that's just minus 4 pi over 3 plus I sine minus 4 pi over 3. So does that give an exact value or not? Well, let's just have a look. Now, I'm just going to use a calculator, even if it is an exact value, which it probably is. What's the point of spending time on this? So cos minus 4 pi over 3 is minus a half. So I've got 256a to the 8 minus a half plus I sine, well, I might as well work out my sine. So the sine a minus 4 pi over 3. I know that's root 3 over 2, but you can press SD in the calculator to tell that me. So that's root 3 over 2. So then let's just simplify that out a little bit. Well, we can take a half out as a common factor, I suppose. So that just gives me 128a to the 8 minus 1 plus root 3i. And then let's just check how we want it. Or I'll write it exactly the same way we want it. Minus 1 plus I root 3. And we're done there. Now you might be wondering, how would you work out minus 4 pi over 3 cos as an exact value? There's a couple of rules you can remember, but forgetting about remembering rules, cast diagram. Let's see, if you think about minus 4 pi over 3, well, that's minus 4 times 180 divided by 3. That's minus 240 as an angle. Now, that's a funny angle, but we can get that into a normal angle by saying, well, it's just the same as 120. So if I just look at the cos of 120, I will get the same answer. Cos of, let me just put my thing in degrees, 120 is minus a half. Sine of 120 is root 3 over 2. So if you just worked out those two using a cast diagram to realise that 60 is a related angle, then you'll be happy enough there. Question 3, given that z1 is 5 plus 3i, z2 is 6 plus 2i, express z1 times the complex conjugate of z2 in the form a plus ib, where a and b are real numbers. So we've got the complex conjugate of z2 is just 6 minus 2i. So z1 times z2 bar is just going to be 5 plus 3i. 6 minus 2i, expanding the brackets, so we get 30 minus 10i plus 18i minus 6i squared. But remember, I squared equals minus 1. So z1, z2 bar is going to Advanced Higher Maths 2023, paper 2, question 14. A complex number is defined as omega is equal to, or w equals a plus ib, but a and b are positive integers, and w squared or omega squared is equal to 6 plus 8i. Determine the values of a and b. Okay, let's start this one. So we've got a plus ib, and that means, and we've also got squared is 6 plus 8 plus 6i. Well, obviously, w squared is equal to a plus ib all squared, so we can say that. A plus ib all squared. Well, multiplying out those brackets, that gives us a squared plus 2abi, and then it'll be minus b squared because I squared is minus 1. That's going to equal 6 plus 8 plus 6i, sorry. So equating the real and imaginary parts together, that gives us some logic to say that a squared minus b squared, the real part, must equal 8, and obviously 2ab must equal 6, the imaginary part of this. Right, and b in terms of a, that means that b is 6 divided by 2a, or 3 over a. We can now sub that into our other side, so using that fact, we've got a squared minus 3 over a all squared equals 8. So that's a squared minus 9 over a squared equals 8. So timesing through by a squared, you get a to the power of 4 minus 9 equals 8a squared. Taking everything to the left so we can solve that, we get a to the 4 minus 8a squared minus 9 equals 0, which is a bit like a quadratic, really. So we've got double brackets for this one. A squared and a squared for our terms. So two numbers at times together to make 9, but add together to make 8 is 9 and 1, of course. So it's minus 9 plus 1. So we now know that implies that a squared must plus 1 equals 0, or a squared equals 9. And that implies
we can disregard that one because a is greater than 0. And for this one, we can say that this implies that a equals 3 because a is greater than 0. So we've got our a, so now we need to get our b. Well, b is 3 over a. So b is equal to 3 over a, 3 over 3, which is 1. We've got our two answers for A and B, and so we're done there.
SQA Advanced Higher Maths 2024, Paper 2, Question 12. Given that z equals x plus iy, where y is not equal to 0, solve that equation, where z bar is the complex conjugate of z. That's nice of them telling us. We should know this anyway. So we'll just sub it in and just solve. No big deal, surely. X plus iy squared plus 20x minus iy, because it's a complex conjugate, minus 156 equals 0. So let's just see where we get with this. X squared plus 2xyi plus I squared y squared plus 20x minus 20yi minus 156 equals 0. Let's collect all the real terms in the same bit together. So we've got x squared plus 2xyi minus y squared, because I squared is minus 1, plus 20x minus 20yi minus 156. And think of that, 0 is 0 real plus, well, 0 imaginary either. So 0 plus 0i, you can think of that as. So you can just say that the real part, so looking at the real part of this side, you've got x squared minus y squared plus 20x minus 156 equals 0. And then looking at the imaginary part, you've got 2xy, and then you've got minus 20y, and that equals 0. So we can just solve them simultaneously. So looking at the imaginary part, because that's a simple one to solve, 2xy equals 20y, so y's cancel, 2x equals 20, we've got x is 10 straight away. We know x is now 10, so we can just do 10 squared minus y squared plus 20 times 10 minus 156 equals 0. 100 minus y squared plus 200 minus 156 equals 0. So that's 300 minus 100 is 200 minus 56 is 144. So you get minus y squared plus 144 equals 0. You can solve that directly or with double brackets, it's your choice. I'll just do it directly. Y squared is 144. That implies y equals the root of 144, but plus and minus. So y equals 12, or y equals minus 12. Z is x plus iy. So Z1, first solution, x is 10, 10 plus 12i. And the second solution must be the complex conjugate, which it is 10 minus 12i. Two solutions for a quadratic, so we're done there.
Question 7, the complex number z equals 3 plus I is the root of z squared minus 6z plus a, where a equals 0, where a is a real number. Part A, nice and simple, state the second root of z squared minus 6z plus a equals 0. Well, that is just going to be z equals 3 minus I. In other words, the complex conjugate of our original z. Part B says, hence otherwise find the value of a. So we've got our complex divisors, so we've got z minus 3 plus I times z minus 3 minus I. So we can expand our brackets in the normal way. So that gives us z squared minus z times 3 minus I minus z times 3 plus I minus 3 plus I 3 minus I. It'll be a plus actually, because minus times a minus is a plus. So that implies we've got z squared minus 3z plus iz minus 3z again minus iz plus 9 minus 3i plus 3i is nothing, minus I squared. So that implies that we've got z squared minus 6z. These cancel each other. Plus 9. And then I squared is minus 1, so plus 1. Because remember, I squared equals minus 1. So that implies we've got z squared minus 6z plus 10. And our original, remember, was z squared minus 6z add a. And therefore, a equals just the number 10. 6c, the expression z squared minus 6z add a is a factor of z cubed minus z squared minus 20z add b, where b is a real number. Find the value of b. So since it's a factor, we can just divide. And since it is a factor, the remainder will be 0. So we can just do that. So let's set up our long division. We've got z cubed minus z squared minus 20z plus b divided by z squared minus 6z plus 10, because a is 10, remember, we've just worked that out. So z squared goes into z cubed z times. Times and through by z, then we get z cubed minus 6z squared plus 10z. Taken away from each other, that gives us nothing, and it gives us 5z squared, and we get minus 30z plus our b on the end. So z squared, that's squared, sorry, 5z squared. Z squared goes into 5z squared 5 times. So that gives us 5z squared minus 30z plus 50. Take them away then. That's nothing. That's nothing. And that gives us b take away 50. But remember, z squared minus 6z plus 10 is a factor. So that implies the remainder must equal 0. So that implies b minus 50 equals 0, and therefore b equals 50. And with complex numbers, SQA Advanced Higher Maths 2017 question 17. The complex number z equals 2 plus I is a root of this polynomial equation, which is a 4th power one. State the second root. Well, part A, that's really easy. That is just 2 minus I. So, nice and easy to start with. Now it says, find the value of q in the remaining root. So you'll see I've got a z4 minus 6z cubed plus 6z squared minus 22z plus q equals 0. So I'm going to have to find a quadratic factor. So I've got z minus 2 plus I, all times by z minus 2 minus I. So that's going to be times to get a quadratic factor. So multiplying it with these brackets and working it out, I get z squared. And then I get minus 2 minus I times z. Let me just write it out for you in case you need it. Minus another 2 plus I times z. And then you get a minus times a minus is a plus. So plus 2 plus I and 2 minus I, which is the difference of 2 squares. So that gives me z squared. And then if you look at multiplying out these brackets here, you've got minus 2z is minus 4z. But then you've got minus and minus is plus I, minus I, z. So they just cancel out. And then we just get this difference of 2 squares. 2 2's is 4. And then minus and plus cancel, so you get minus I squared. So finally you get z squared minus 4z, but because I squared is minus 1, I get 4 plus 1 is 5. And there is my quadratic factor there. Part B, so keep going with that. So now I need to do some algebraic long division. So we've got z to the 4 minus 6z cubed plus 16z squared minus 22z plus q divided by z squared minus 4z plus 5.
So it's how many times z squared goes into z to the 4, which is z squared times by z squared to get z4 minus 4z cubed plus 5z squared. Almost forgot the squared there. Take away. That's 0, of course. Minus 6 plus 4 is minus 2z cubed. 16 minus 5 is 11z squared. And I've still got minus 22z plus q. And start again. Z squared into minus 2z cubed is minus 2z. Times through by minus 2z. Minus 2z times z squared is minus 2z cubed. Minus 2z times minus 4z is plus 8z squared. And finally, minus 2z times 5 is minus 10z. Take away again. Minus, that's 0. 11 minus 8 is 3z squared. Minus 22 plus 10 is minus 12z. And then we've got q at the end. We're still in z squared and z squared, so we can go again. Z squared into 3z squared is plus 3, of course. So you get 3z squared. And then you get 3 fourths is 12z, minus, of course. And 3 fives is 15. Take away one last time. That minus that is 0. Minus 12 plus 12 is also 0. So you get q minus 15. So there's our remainder. But since these are factors, then that equals 0. So that means we can just say straight away that therefore q equals 15. And the remaining roots. So the remaining roots then, we've got z squared minus 2z plus 3. So let's say that z squared minus 2z plus 3 equals 15. Equals 0. Don't know why I'm saying 15. Where did I get that nonsense from? So does that factorize? Well, let's hope so. 3 times 1 is 3, plus 3 minus 3. Nah, it's not going to factorize. So quadratic formula, z equals minus b, plus or minus the square root of b squared minus 4 times a times c all over 2a. Or you could complete the square if you prefer. So you get z equals 2 plus or minus 2 2s is 4, 4 3s is 12, 4 minus 12 is minus 8, root minus 8. Why did I write 2a up here? 2 times 1 is 2, so all over 2. So that is 2 plus or minus, well, that's a sort, isn't it? So root 4, root 2, root minus 1 over 2. 2 plus or minus 2 root 2, square root of minus 1 is I, all over 2. And finally we get 2, well, that's just 1 then, plus or minus root 2i. So to be very clear, that's our 2 remaining roots. So we're done there. Question C, show the solutions to this on an Argand diagram. So we've got 2 plus I and 2 minus I. So for part C, we've got 2 plus I, 2 minus I, and then 1 plus root 2i, and 1 minus root 2i. Putting them on an Argand diagram. Remember, that's just an imaginary and real axis. There's real, we'll say, and there's imaginary. Let's say along 2 is here, and up 1 is there. So that's 2, 1. And then 2 minus I will be symmetrical, so let's put minus 1 down there. 2 minus 1. And then 1 plus root 2i. Well, root 2 is bigger than 1. So it's going to be along 1, up root 2, and down root 2. So let's just put root 2 is here and here. It doesn't have to be too exact, but clearly these need to be above it and below it. So 1 root 2 and 1 minus root 2. And we're done there. SQA Advanced Higher Mathematics 18, question 10. Complex numbers, given z equals x plus iy, sketch the locus in the complex plane, given by modulus of z equals the modulus of z minus 2 plus 2i. There are various methods to accomplish this task. The method that I prefer is to take the modulus of both sides and go through and equate it and see what you get. So the modulus of z is x plus iy equals the modulus of, well, x plus iy again, minus 2 plus 2i. So I can then simplify that. X minus 2 is the real part, and then I is a common factor, so I get plus y plus 2i. So then taking the modulus means to square the real and imaginary parts in square root. So I can write that equals the square root of x squared plus y squared equals the square root of, well, the real part is all of that, and the imaginary part is that bit. But then with square root both sides, so just get rid of the square roots, they cancel. So you get x squared plus y squared equals, I'll expand the first bracket, x squared minus 4x plus 4 plus second bracket y squared plus 4y plus 4. Well, I've got x squared on both sides, so they cancel. Y squared on both sides, so they cancel. So 0 equals minus 4x plus 4y. 4 plus 4 is 8. So that's equation a straight line. Take the 4y on its own to equal 4x minus 8. Divide by 4. Y is x minus 2. So then we need to sketch that. So imaginary and real diagram. So there's my imaginary and there's my real. So it goes through some points, cutting the y-axis. It cuts the y-axis next to 0, so it cuts at minus 2. And it cuts the x-axis when y is 0. So that was when x equals 2. And there we are. Question 12, let z equal cos theta plus I sin theta. Use the Moivres theorem to state an expression for z4. So part A, nice and simple. Z4 is simply cos 4 theta plus I sin 4 theta. 1 mark. No real problem there. Question B, state and simplify the binomial expansion of cos theta plus I sin theta to the power of 4. So we've got cos theta plus I sin theta to the power of 4. I'll need quite a bit of space for this one. So we've got 4 choose 0 of cos 4 theta. And then we'll have 4 choose 1 cos cube theta. I sin theta. And then we'll have 4 choose 2 of cos squared theta. I sin theta squared, which we'll work out in a minute. 4 choose 3 of cos theta. I sin theta cubed. And lastly, 4 choose 4 of just I sin theta to the power of 4. Remember, I is, so tidying this up, so 4 choose 0 is 1, so we've got cos to the power of 4 theta. 4 choose 1, well, that's 4 factorial over 1 factorial, 3 factorial if you were taking your time, which is just 4. So you've got 4i. Cos cube theta sin theta. Then you've got 4 choose 2, so that's 6. And then it's cos squared theta sin squared theta. But it will be minus because I squared is minus 1.
Moving on to our next one, 4 choose 3. So that's 4 again. So we're going to have 4 cos theta sine cubed theta. And I cubed, well, I squared is minus 1. So minus 1, and then I've still got an I. So minus 4i. And the last one, 4 choose 4, is just 1, of course. I to the power of 4 is I squared is minus 1, so minus 1 times minus 1 is plus 1. So we're just going to have plus sine to the power of 4 theta. Part C says, hence show that cos 4 theta equals 8 cos to the power of 4 theta minus 8 cos squared theta plus 1. So part 1, we already know that cos theta plus I sine theta to the power of 4 from the Moivres theorem is cos 4 theta plus I sine 4 theta plus 4i cos cubed theta sine theta minus 6 cos squared theta sine squared theta minus 4i cos theta sine cubed theta plus sine to the power of 4 theta. So we can see that this is made up of a real part and an imaginary part. So if we just equate the real parts, we'll end up with cos 4 theta. So equate the real parts. So that implies that we've got cos 4 theta equals cos to the power of 4 theta. Second term is imaginary. Minus 6 cos squared theta sine squared theta. Next term is imaginary, but then we've got plus sine to the power of 4 theta. So cos 4 theta equals cos to the power of 4 theta minus 6 cos squared theta. Sine squared theta is 1 minus cos squared theta. And since sine squared theta is 1 minus cos squared theta, then we'll have plus 1 minus cos squared theta squared, because sine to the power of 4 theta is sine squared times sine squared. So now we've got everything in terms of cos. Tidying that up further, we've got cos to the power of 4 theta minus 6 cos squared theta plus 6 cos to the power of 4 theta plus 1 minus 2 cos squared theta plus cos to the power of 4 theta. So cos 4 theta equals 1, 6, 8 cos to the power of 4 theta minus 8 cos squared theta plus 1 as required. Okay, part 2, sine theta cot 4 theta can be written in terms of cos theta only. So sine theta cot 4 theta, well, that's just sine theta times the cos of 4 theta over the sine of 4 theta. So that equals sine theta 8 cos to the power of 4 theta minus 8 cos squared theta plus 1 all over sine 4 theta. Okay, part B told us that cos 4 theta plus I sine 4 theta equals, I'm just going to paste this in. So if we want to know what sine 4 theta is, we can just equate the imaginary parts, because we've got an I here, to the imaginary parts of this hand side. So equating imaginary parts, sine 4 theta must equal 4 cos cubed theta sine theta minus 4 cos theta sine cubed theta. Subbing it in, remember that's what we've got. That's going to be sine theta 8 cos to the power of 4 theta minus 8 cos squared theta plus 1 all over 4 cos cubed theta sine theta minus 4 cos theta sine cubed theta. Taking sine theta out as a common factor on the top, we've still got, but taking it out on the bottom as well so we can get rid of the sines. So sine theta is a common factor. So it's 4 we get cos cubed theta minus cos theta sine squared theta. Sines cancel, of course. So on the top we get 8 cos 4 theta minus 8 cos squared theta plus 1 over 4 times cos cubed theta minus cos theta times 1 minus cos squared theta for sine squared theta. And that equals 8 cos 4 theta minus 8 cos squared theta plus 1 over 4 cos cubed theta minus cos theta plus cos cubed theta. That equals 8 cos to the power of 4 theta minus 8 cos squared theta plus 1 over cos cubed plus cos cubed 2 cos cubed 8 cos cubed theta minus 4 cos theta.
Complex numbers, SQA Advanced Higher Mathematics 2019, paper 1, question 18. Complex numbers have been plotted on an Argand diagram, express W in Cartesian form. W equals, well, on the real part it goes along A, and on the imaginary part it goes down minus A root 3, minus A root 3i. And then we need to get that into polar form. So polar form means we need the modulus in the argument. So let's just start working on that. So for part 2, the modulus is just the real part squared plus the imaginary part squared, square rooted. So that's just a squared plus 3a squared, which is 4a squared. So that gives me 2a. And then our argument, tan theta, is equal to minus a root 3, imaginary part, over the real part, which is just minus root 3. And we know that it's in the fourth quadrant down here, because of where it's drawn already. Now this was paper 1, so we are looking at exact values here. So if I draw an exact value triangle, you've got pi over 3 and pi over 6. 1, 2, root 3. So if I take root 3, pi over 3 is my related angle. So looking at a cast diagram and thinking about root 3 as being pi over 3, we know we're in here, so we're 2 pi minus pi over 3. So 2 pi is 6 pi over 3 minus pi over 3, which is 5 pi over 3. So we could leave it as 5 pi over 3, or a principal argument, which is usually nicer, but you don't necessarily have to leave it like that, would be 5 pi over 3, and then you just take away 2 pi to get it in between minus pi and pi, you see? So minus 2 pi, which kind of undoes that one as well, you see. So you've got 5 pi over 3 minus 6 pi over 3, which is minus pi over 3, which is very nice. So then our final answer in polar form then is that W equals 2a cos theta minus pi over 3 plus I sine minus pi over 3. And we're done there.
Part B. The complex number z1 is a root of z cubed equals w, where z1 is k cos pi over m plus I sin pi over m for vectors k and m. And given that a equals 4, use the Moivres theorem to find the values of k and m. Okay, so let's start working on part B. So we're telling us that a is 4, so that means that w is equal to 8 cos minus pi over 3 plus I sin minus pi over 3. And it's the roots of z cubed. So then we can just work out, if it's the roots of z cubed, we can say that we can cube root it. So z cubed equals omega. Let's just write that here. So that means by de Moivre's theorem, z, say 1, is equal to omega to the third cube root, which is 8 to the third cos times by a third, so minus pi over 9, plus I sin minus pi over 9. So that equals 2 cos minus pi over 9 plus I sin minus pi over 9. And then let's just check what the question was actually asking us to write. K and m. Write it down. So k equals 2 and m equals 9, I think. Minus 9 in this case, actually, because it says k and m are integers. And it's got pi on the top, so the minus is going with the 9. So there you are, minus 9 and 2. Part 2 says find the remaining roots. So let's have a look. We want the remaining roots. What's z1? So for part 2, to get z2, there's two ways to do this, really. You can either start it here and add 2 pi, and then, well, divide by 3. So, cube root it, so times it by a third. Or you can just start with already being a thirded, but then you add 2 pi over 3, okay? So that's the two ways to kind of think about this. So let's have it that way. So you've got 8 to the third cos minus pi over 9 plus 2 thirds for our first one, plus I sin minus pi over 9 plus 2 thirds. So we need to then work that out. Well, we're holding on 8 to the third is 2. Shouldn't have gotten that again, actually. So common denominator, this times that through by 3 to get 6 on the top. That's a pi there, by the way, a pi. So you've got 6 minus 1 is 5. 5 pi over 9. Plus I sin 5 pi over 9. And there's your first root. So for z3, that's just going to be 2 cos, well, you've got 5 pi over 9 again, plus 2 pi over 3, plus I sin 5 pi over 9 plus 2 pi over 3. Or what you could have done if you preferred would be to go to the original z1 and take away 2 pi over 3, so you'd get a consistent spacing between them. But I've done it now this way, so I'm just going to continue. So 5 pi over 9 plus 6 pi over 9, well, 5 plus 6 is 11 pi over 9. Plus I sin 11 pi over 9. And you'd probably be fine leaving it like that, but just to be on the safe side, I'll turn that back into the principal argument by taking away 2 pi's. So that would give me 2 pi is minus 18 pi over 9, just to be clear on the brackets here. So 11 minus 18 is minus 7 pi over 9, plus I sin minus 7 pi over 9. And we're done there. SQA Advanced Higher Maths 2024 Paper 2 Question 2. Use the Euclidean Algorithm to find integers a and b such that 533a plus 455b equals 13. Same thing again. We're going to find the GCD of 533 and 455.
So 533. Well, that is 15455s, I suppose, plus some sort of remainder, which I can't be bothered working out. 533 minus 455 is 78. Divided by the remainder, 455 equals 578. 578 says 390. That gives me 65 remainder. So 78, that's an 8, equals 165s plus 13. Divided by the remainder, 65 is equal to, what much, 4 of them, isn't it? 5 of them, 5 13s. So the GCD is 13. So now we can, 13 is what the right hand side is, so we can start from here and work backwards. 13 equals 78 minus 165. Go up the list. But that means we get 78 minus, and I'm just rearranging the remainder, remember? So 1 times 455 minus 578. Expand and simplify. So I've got minus 1 times minus 5 is plus 5, plus another one is 6 of them, 6 7/8, minus 1 455s. And we'll just keep going with this. So I'll move up the list, rearrange the 78 to 533 minus 1 455. So 6 lots of 533 minus 1 455s. And I've still got minus 1 455s hanging about on the end, to finally give me 6 times 533. Minus 6 minus 1 is minus 7 of them. Remember that equals 13. So my A is 6 and my B is minus 7. And we're done there.
SQA Advanced Higher Maths 2023, paper 2, question 6. Use the Euclidean Algorithm to find D, the greatest common divisor between 703 and 399. Okay, part A, so D between 703 and 399. So we've got 703, well that is going to be 1 times 399, and then to get your remainder, take away 399 and you get 304. And then we just start again. So 399, that's equal to 1 304s, and the remainder in this case is 95. Starting again with 304, well this time that is going to be 395s, if you're not sure, use a calculator, and the remainder from that is 19. So then finally 95 is 5 19s, so 0 remainder, and therefore D is equal to 19. And we're done for part A. Part B, find integers A and B such that D is equal to 703A plus 399B. So for part B, D equals 703A plus 399B. So D was 19, so starting from this line, 19 equals 304 minus 395s. 19 equals 304 minus 3 times 95. And then we can just keep jumping up. That means that 19 equals 304 minus 3 times whatever 95 is. Well, 95 we'll get from the next line. 399 minus 304. 399 minus 1 times 304. And that equals, well, we've got 304 minus plus 3 304s. So that's 4 times 304 minus 3 times 399. And then moving on to our next line, well, 304 is 399 minus 95. So that means that 19 equals 4 times 399 minus 1 times 95. I suppose I could put 1 times, and that's minus 3 times 399. So we can simplify that to 4 lots of 399 minus 3 lots of 399 is 1 lot of 399 minus 4 lots of 95. So moving up again, 304 is 703 minus 399. So that means that 19 equals 4 times 703 minus 1 times 399. And we've got minus 3 times 399 still. So that 19 equals 4 times 703 minus 4 399s minus 3 399s is minus 7 times 399. So A is equal to 4 and B is equal to minus 7. And we're done there. Part C, hence find interest P and Q such as 76 equals 703P plus 399Q. So notice the connection between 76 and 19. 4 19s is 76. So that means that I can say that at the side, I suppose that 76 equals 4 times 19. So 76 is equal to 4 times the whole thing answer we just got, which is 4 times 703 minus 7 times 399. So that means that 76 is equal to 4 times 4, which is 16, times 703. 4 sevens is 28, minus 28 times 399. In other words, P equals 16 and Q equals minus 28. And we're done there. SQA Advanced Higher Maths 2023, Paper 2, Question 9. Express 572 base 10 and base 9. So we've got 572 in base 10. So what does that mean? That means 5 times 10 squared plus 7 times 10, I suppose, plus 2. Now we need to express this in base 9, so we can just repeatedly divide by 9. Okay, so we've got 572 divided by 9. So 9 sixes is 54. 54 for 5, 6, 7, 3 left over. 9 threes is 27. 27, 28, 9, 30, 1, 32, remainder 5. So we get immediately 572 divided by 9, right here, is equal to 63, remainder 5. So then we can just divide 63 by 9. Well, 63 by 9 is pretty simple. It's 7, remainder 0. And then taking our 7 divided by 9, well, we get no 9's going to 7, so 0. And we've got a remainder of 7. And therefore, we can just read it backwards, 705. So 572 in base 10 is equal to 705 in base 9. And we're done there.
Changing bases, some past paper questions. 2019, question 12 says change 231 base 11 into base 7. So we need to change from base 11 to base 10, then from base 10 to base 7. So how do we change to base 10? Well, 231 base 11 is just equal to, if we think in terms of 11 powers, 11 to the power of 0, I'll have 1 of them. 11 to the power of 1, I'll have 3 of them. And 11 squareds, we'll have 2 of them. Just like the tens, hundreds, thousands columns. So 2 11 squareds plus 3 11s plus 1, because 11 to the 0 is 1 as well. 11 squares is 121 times 2 is 242 plus 3 11s is 33 plus the 1 is 276. So that's 276 base 10. And now to change the base 10 number into base 7, we just constantly divide by 7. So let's start from here. 276 is equal to something times 7. 276 divided by 7, well, that's 39, plus 273, 3. So divide 39 by 7, not the remainder this time, this one. That's 5, plus 4. So divide the 5 by 7, Well, that's 0. So I've got 5 left over. As soon as I get 0 in this position, I'm done. So I just read it up the way in base 7, 2, 3, 1, base 11 equals 5, 4, 3, base 7, and we're done there. SQA Advanced Higher Mathematics 2024, Paper 2, Question 11. Consider statements A and B below. For each statement, if true, provide a proof, and if false, provide a counterexample. Okay, statement A. The sum of the squares of any two consecutive numbers is always prime. I'm thinking Pythagoras here. 3 squared plus 4 squared equals 25. Well, 25 is not prime. There you go, counterexample, job done. 3 squared plus 4 squared equals 9 plus 16 plus, which equals 25. 25 is not prime, therefore it's false. I'm sure there's other examples, but that one will do. Okay, the sum of any two consecutive integers is always odd. Let's see if that is true by saying that, look, let's let n be an integer, and then the next one is n plus 1 then. So you're going to have n squared plus n plus 1 squared. And just a reminder, looking at odd, the form you're looking for is 2a plus 1 is odd, or 2n plus 1, whatever. Expanding the bracket, we get n squared plus 2n plus 1, which is 2n squared plus 2n plus 1. So taking out a common factor with 2 from the front bit and n, or just 2 even, we'll get n squared plus n plus 1, and that's just a number. So that's just basically of the form 2a plus 1. So we can just immediately say that equals or is of the form 2a plus 1, therefore odd, so statement true. And we're done there. Example 14, SQA Advanced Higher Mathematics 2023, Paper 1, Question 8. Part A, consider the statement for all integers a and b, if a is less than b, a squared is less than b squared. Find a counterexample to show that it is false. And then part B, let n be an odd integer, prove directly that n squared minus 1 is divisible by 4. Let's deal with these separately then. Let's go for a first. So we want to pick a number a less than b such that a squared is less than b squared. Now let's think about positive numbers first, see how you would work through this. Let's pick 1 and 2. 1 1s is 1, 2 2s is 4. It's not going to work. What about negative numbers then? That's going to give us something. Let's say that a was minus 1 and b was 2. Well, minus 1 squared is 1, 2 2s is 4. That's not worked either. But what about a being a bigger negative number? So let's say we had a was minus 3. Minus 3 squared is 9. Then all I need to do is pick a b smaller than a b bigger than that, any positive number, which is about 1 or something, and it will be done. So let's say let a equal minus 3 and b equal to 1. Then minus 3 is less than 1, but minus 3 all squared is 9. 1 squared is 1, and 9 is not less than 1. And we're done there. Therefore, false. Okay, part B, let n be an odd integer. Let n be an odd integer. Remember, that's how you write an odd. Prove directly that n squared minus 1 is divisible by 4. So we want to prove that if we take n squared minus 1, you get a multiple of 4, 4 times anything. So let's just look at n squared minus 1. N squared minus 1 equals 2k plus 1 all squared minus 1. That's 4k squared plus 4k plus 1, then minus 1. Well, that's just 4k squared plus 4k, but that's a multiple of 4. Don't take out k as a common factor. You only need to take out your 4, since we know that 4 is 4 times k squared plus k. That's a multiple of 4. As k, remember, was a member of z. So you're doing, if k is an integer, k squared plus k is also an integer, of course, a whole number. So that means that 4 times a whole number is a multiple of 4. So therefore, true. Therefore, what we're trying to prove again, that is divisible by 4. Well, that's it. Done. Example 8. Use the contrapositive to prove that if n squared is a multiple of 3, then n is a multiple of 3. So we're looking to see what contrapositive means here. So the contrapositive is using not. So not, if n is not a multiple of 3, then n squared is not a multiple of 3. That's our contrapositive statement. Kind of working backwards, n squared is a multiple of 3, then n is a multiple of 3. So if n is not a multiple of 3, n squared is not a multiple of 3. If we can prove that, then by proof by contrapositive, we have actually proved n squared is a multiple of 3, then n is a multiple of 3. So that's what we're trying to do. So we're saying that if n is not a multiple of 3, so n does not divide 3, we'll say if. And we'll consider the two cases. The remainder when n is divided by 3 is either 1 or 2. If you think about it, if you divide a number by 3, it's either going to go in exactly, or you're going to have one remainder or two remainder. So the remainder when n is divided by 3 is either 1 or 2. So let's just check both cases, right? So remainder 1. That implies that n equals 3k plus an extra 1 for some k a member of z. So in this case, n squared would be 3k plus 1 all squared. Well, that equals 9k squared plus 6k plus 1. Now all we need to say is that 3 times the number plus 1? We'll just take 3 out as a common factor and leave the 1 on the end. So that equals 3k squared plus 2k, with an add 1 sitting about on the end waiting. So n squared is 1 greater than a multiple of 3, so that means that 3 does not divide n squared. One greater than a multiple of 3, then for 3 doesn't divide n squared. And then we'll just check what happens when the remainder is 2. So for remainder 2, n must equal some number 3k plus 2 for some k a member of z, and that means that n squared would be 3k plus 2 all squared, which is 9k squared. 3 2s is 6 times 2 is 12k plus 4. So again, can we check to see if that equals plus 2 or something? So what does that equal? 3 times what? Well, 3k squared plus 4k. We can take out, well, 3, and we can take out a plus 1 here. 3 ones is 3, and then have 1 on the end. So we've still got a remainder of 1 at the end. So in this, the second case, n squared is 1 greater than a multiple of 3. Therefore, 3 does not divide n squared. So we've exhausted both of the cases, and each of them 3 didn't divide n squared. So we've proven that if 3 doesn't divide n, it doesn't divide n squared. So the contrapositive is true. We just need to write that down. So we have proven that if 3 doesn't go into n, then 3 doesn't go into n squared, and therefore we have by the contrapositive, which we would need to write, if 3 divides n squared, then 3 divides n, and we're done there. Example 9, prove by contrapositive that if PQ is irrational, then at least one of P or Q is irrational. So what is our contrapositive statement? If both P and Q are rational, then P and Q is rational. So let's write out our contrapositive statement. If, now or becomes and, both. If both P and Q are rational, then P times Q is
rational. So what does it mean for P and Q to be rational? It means we can write them as fractions. P is equal to some number A over B, and Q is equal to some number C over D, where A and C we would want to be integers. It can be anything, positive or negative, but we want B and D to be natural numbers because we don't want to get a negative divided by a negative. So we've got that. What is P and Q? Well, P times Q is A over B times C over D. That's AC over BD. Well, what's our top? Our top's an integer. She times an integer together, and our bottom's a natural number. So that's also a member of Q, just by looking at it, okay? And we've just then therefore proven that if P and Q are a member of Q, then PQ must also be Q. P times Q is also a member of Q. So by the contrapositive, the opposite is true. So by the contrapositive, if PQ are not rational, so not, then P times Q is not rational. And we're done there.
Advanced Higher Maths 2023, Paper 1, Question 7. Find an expression for the sum of 1 to n of r squared plus 3r in terms of r, and expression answer in this form. So again, from the start of the exam paper, the sum of r equals 1 to n. Well, we've got two there. We've got r squared plus 3 times the sum of r equals 1 to n of r. So you can actually just use that exam paper for this if you don't memorize this stuff. R squared is n plus 1 to n plus 1 over 6. And plus 3 times the sum of r equals 1 to n is just n plus 1 over 2. That's an n over 2. And then we can just tidy that up. So making it r to 6, we get n plus 1 to n plus 1. Times in this second fraction by 3, we get 9n n plus 1, and that's all over 6 then. Taking out n plus 1 as a common factor, we've got 2n plus 1, and then n plus 1, so plus 9, all over 6. That's n plus 1, 2n plus 10, all over 6. And it says leave it divided by 3 or a third. So I want to take a third out, n plus 1. So I've divided the bottom by 2, so I can divide the top by 2 to get n plus 5. And we're done there. Part B says, hence I always find the sum of I equals 11 to 20 of r squared plus 3r. So part B, the sum of r equals 11 to 20 of r squared plus 3r is equal to the sum of r equals 1 to 20 of r squared plus 3r minus the sum of r equals 1 to 10 of r squared plus 3r. And we've got a third n plus 1, n plus 5 for r equals 1 to n. So n is 20 in the first one, so we've got a third of 20. 20 plus 1 is 21, 20 plus 5 is 25, minus, and then our n equals 10, so we've got a third of 10 times 11 times 15. So we'll do a little bit of math. 21 divided by 3 is 7, so we've got 7 times 20 times 25, minus 15 divided by 3 is 5, 5 times 10 times 11. 10 25 is 250, times 2 is 500, 7 times 500 is 3,500 for the first term,
5 times 10 is 50, times another 10 is 500, plus 1 is 550. 3,500 minus 550 is 3,950. And we're done there. SQA Advanced Higher Maths 2023, Paper 2, Question 12. Prove by induction that for all positive integers n, the sum of y equals 1 to the n of 2 to the r minus 1 times r is 2 to the n minus 1 plus 1. So let's prove it for n equal to 1. Let's prove. And then we'll do for k, and then k plus 1 should follow. So for the left-hand side, we get r equals 1 to 1 of 2 to the 1 minus 1 times 1. Now that gives us 2 to the 1 minus 1, 0, so 2 to the 0 times 1, which is just 1. And the right-hand side should follow. We get 2 to the n equals 1, 1 minus 1 plus 1. That's 2 times 0 plus 1, which equals 1. So it's true for n equal to 1. And now we're going to assume it's true for n equal to k. So assume true for n equal to some number k. So we can write the sum, that means the sum of I equals 1 to k of 2 to the r minus 1 times k times r equals 2 to the k minus 1 plus 1. And now we want to prove it for n equal to k plus 1. So we're going to prove for n equal to k plus 1. So let's look at k plus 1 then. Looking at our left-hand side, that will give us the sum of r equals 1 to k plus 1 of 2 to the r minus 1 times r. And the game here is, I suppose, to pull this out to see if we can get some sort of composite sums that are add or take away, but we already know the answer to. So what does that equal? Oh, equal the sum of r equals 1 to k of 2 to the r minus 1 times r plus the k plus 1th term. Well, what is the k plus 1th term? It's going to be 2 to the k plus 1 minus 1 times k plus 1, because that's the k plus 1 when that r is k plus 1. So then we'll just tidy that up. We already know the sum of I equals 1 to k of 2 to the r minus 1 times r, because we said it was true for n equal to k, so we can sub in this right-hand side. So that gives us 2 to the k minus 1 plus 1. Plus r. Now, we can tidy this up slightly. That's k plus 1 minus 1, which is 2k, just k, 2 to the k times k plus 1. So we've got 2 to the power k as a common factor. We can just leave the 1 on the end. So that means we've got 2 to the power k, and we've got k minus 1 plus k plus 1. And we've got our plus 1 hanging around the end. So we can tidy that big bracket up. We've got k plus k is 2k, minus 1 plus 1 is 0, plus 1. 2 to the k times 2k, well, basically that's 2 to the 1, so we can add the powers, so that gives you 2 to the k plus 1 times k plus an extra 1 on the end. So that's our left-hand side. Now I suppose it's worth looking at what our right-hand side would be. So if we look at our right-hand side of this, we have got 2 to the n minus 1 plus 1. Let's just write that down. 2 to the n minus 1 plus 1. So this doesn't look quite like that, but when n equals k plus 1, that implies we get 2 to the k plus 1, k plus 1 minus 1 plus 1, which is the same as 2 to the k plus 1. K plus 1 minus 1 is just time k plus 1. So we've got the same result from the left and the right, and therefore the sum of r equals 1 to k plus 1 of 2 to the r minus 1 times r equals 2 to the k plus 1 minus 1 plus 1. Just write a little statement to say it's true for n equal to k, and implied it was true for n equal to k plus 1. And since it was true for n equal to 1, then by induction, it will be true for all n a member of Z plus. And we're done there. Example 13, SQA Advanced Higher Maths 2019, question 14. Prove by induction that the sum of r equals 1 to n of r factorial r equals n plus 1 factorial minus 1 for all positive integers n. So again, we'll start with a base case of n equal to 1. So we've got the sum of r equals 1 to 1 of r factorial r, well that's just 1 factorial times 1, which is just 1. And then the right hand side, we've got 1 plus 1 factorial minus 1, 2 factorial minus 1 is 2 minus 1 is 1. So true for n equal to 1. Assume true for n equal to k. So the sum of r equals 1 to k of r factorial r equals k plus 1 factorial minus 1. For some k, a member of the natural numbers, or z plus, then positive integers, same thing. So then we're going to try and prove that the sum of r equals 1 to k plus 1 of r factorial r equals, well, what's it going to be? K plus 1 factorial minus 1. Well, let's just see what that is so we know what we're aiming for. That's k plus 2 factorial minus 1. So we'll deal with our left-hand side. So looking at our left-hand side, and we'll try and make it look like our right, r equals 1 to k plus 1 of r factorial r. Well, we can use our r equals 1 to k of r factorial r and then just add the k plus 1th term. So that means we've got r factorial becomes k plus 1 factorial and r becomes k plus 1. But we already know what the sum is. It's k plus 1 factorial minus 1. So that equals k plus 1 factorial minus 1 plus k plus 1 factorial k plus 1. And we should be able to see here that k plus 1 factorial is a common factor between these two things. K plus 1 factorial is a common factor. So we can say we've got k plus 1 factorial k plus 1 factorial times 1. And then for this term, we've got plus times k plus 1. And the thing we didn't factor out was the minus 1, so it's just hanging out in the end, waiting to be dealt with. So that equals to k plus 1 factorial times k plus 1 is k plus 2, all minus 1. Well, remember we're trying to get to k plus 2 factorial minus 1, but that is that. If you've got k plus 1 factorial, and then you times by the next one, you've got k plus 2 factorial. So that is equal to k plus 2 factorial minus 1. Then we just write our statement. Proposition true for n equal to k implies true for n equal to k plus 1. Base case of n equal to 1 true. Therefore true for all n a member of the natural numbers, or z plus. By induction. I forgot my induction, honestly. I should have probably written that first. So by induction true. But therefore, that's fine enough. Question 9 says the matrix A is given by 3 minus 2, 0, 1. Prove by induction that A to the n is 3 to the n, 1 minus 3 to the n, 0, 1 for all n a member of the natural numbers. So this is proof by induction. So let's prove for n equal to 1. So if n equals to 1, a to the 1 would be 3 to the 1, 1 minus 3 to the 1, 0, 1. So that equals 3, 1 minus 3, 0, 1, which equals 3 minus 2, 0, 1, which we already know equals a. So we've proved true for n equal to 1. So assume true for n equal to k. Therefore, that would say that a to the k would equal 3 to the k, 1 minus 3 to the k, 0, 1. And now we need to prove it for n equal to k plus 1. So for prove true for n equal to k plus 1. So when n equals to k plus 1, a to the k plus 1, well, that would equal a to the power of k times a, or since we're dealing with matrices, a times a to the k. And we'll just prove one of these. So a to the power of k times a. We already know what a to the power of k is. We've just worked out that that's 3 to the k, 1 minus 3 to the k, 0, 1. And we already know what a is. That's 3 minus 2, 0 and 1. So matrix multiplication. Let's just give ourselves a nice big matrix. So we've got 3 to the k times 3. And we've got this times 0, which is 0. So that's our first element. We've then got 3 to the k times minus 2. And we've got 1 times 1 minus 3 to the k times 1. So plus 1 minus 3 to the k. Our next element, 0 times 3 is 0, 1 times 0 is 0. And our last element, 0 times minus 2 is 0, 1 times 1 is 1. So we need to tidy that up and make it look like a to the k plus 1. So we need k plus 1s appearing. So that equals, well, our first element, 3 to the power of k times another 3 is 3 to the k plus 1. Our second element, we've got minus 2, 3 to the k plus 1, then minus 3 to the k. So if I take 3 to the k out as a common factor of the terms in 3 to the k, that gives me minus 2 take away 1. And I've still got plus 1 on the end. So that's 3 to the k times minus 2, 3 to the k times minus 1. And then we've still got this plus 1 that isn't attached. And then you've got 0, 1, which is what we would need. So that equals 3 to the k plus 1. Minus 2 take away 1 is minus 3. So 3 to the k times minus 3 plus 1, 0, 1. So that's 3 to the k plus 1. 3 to the k times 3. Well, that's just 3 to the k plus 1 again, with a minus, 0, 1. So in other words, 3 to the k plus 1, 1 minus 3 to the k plus 1, 0, 1. That equals a to the k plus 1. So therefore, the conjecture is proved true for n equal to 1, assumed true for n equal to k, and proved true for n equal to k plus 1. So hence, by induction, a to the n equals 3 to the n, 1 minus 3 to the n, 0, 1, for all n a member of the natural numbers is proved. 2. And we're done. Advanced Higher Maths 2024, Paper 2, Question 5. State and simplify the general term of the binomial expansion of this, and then find the coefficient of 1 over x to the 18. So start of the exam paper tells you that n choose r, well it's the sum of, but we're just wanting the general term, a to the n minus r, b to the r. So r in this case is 16, okay? And what's our a and b? Well, a is just 2x squared, of course. B is minus 1 over x cubed. And we can say that n is equal to 16. Now I might as well just change that to minus x to the minus 3 straight away for my substitution. So we've got 16 choose r, 2x squared, 16 minus r, minus x to the minus 3 r. And then we need to just collect the terms in terms of x's and numbers basically. So you've got 16 choose r, you've got 2 to the 16 minus r, x squared to the 16 minus r. So the minus x you can think of as being minus 1 to the r, and then this leaves you with x to the minus 3, so minus 3r. So that's 16 choose r, 2 to the 16 minus r, minus 1 to the r, x to the 2 16s is 32, minus 2r, and then x to the minus 3r, and finally we get 16 choose r, 2 to the 16 minus r, minus 1 to the r, x to the 32 minus 5r, and we're done there. So I find the coefficient of 1 over x to the 18. Over x to the 18 is x to the minus 18. That implies 32 minus 5r is minus 18. So minus 5r is minus 32 minus 42 minus 50. So r is 10. And now we know that. It is easy. We get 16 choose 10. 2 to the power of 16 minus 10 is 6. Minus 1 to the power of 10. And it's just a coefficient, so we don't need to write anything to do with x, it's just a coefficient. 16 choose 10 times 2 to the power of 6, and minus 1 to the power of 10 is 1. So that's just 512, 512, and we're done there. SQA Advanced Higher Maths 2023, Paper 2, Question 5. Write down and simplify the general term of the binomial expansion of 3x minus 2 over x squared to the power of 8. So part A, looking at the start of the exam paper, binomial theorem says if we've got a plus b to the n, that equals the sum of I equals 0 to n of n choose r, a to the n minus r, b to the r. It tells us what n choose r is as well, but we'll just leave that for now. So for our one, we have got 3x minus 2 over x squared to the power of 8. So that is the sum of r equals 0 to 8. And we have now got 8 choose r. And we have got a is our 3x, so 3x to the power of 8 minus r. And our b is minus 2 over x squared, so minus 2 over x squared to the power of r. So our general term is going to be 8 choose r, and then we can separate this out into 3 and x, and same with these, the number part and the x part. So we'll go ahead and do that. So we've got 3 to the power of 8 minus r, x to the power of 8 minus r, times minus 2 to the power of r, times 1 over x squared to the power of r. So that equals or implies we've got 8 choose r. Put the number parts together and the x parts together. Number parts first, we've got 3 to the power of 8 minus r, minus 2 to the power of r, and then we've got x to the 8 minus r, and then 1 over x squared is x to the minus 2, so x to the minus 2 to the r. Now you can take your time on this, or you can get there a little bit quicker. That gives us 8 choose r. 3 to the 8 minus r. Minus 2 to the r. And then putting the x parts together, rules of indices state if it's the same base, we can add the powers. So we've got 8 minus r minus 2r. That's x to the 8 minus r minus 2r minus 3r. Part B says, hence otherwise determine the coefficient of x to the minus 1. So if we're going to coefficient of x to the minus 1, that means that this bit's minus 1. So we've got 8 minus 3r equals minus 1, and we can therefore solve that for r. That means that minus 3r equals minus 9, or in other words, r is equal to 3. So when r equals 3, we can use our we can just sub that into here. So our coefficient is going to be 8 choose 3. 3 to the power of 8 minus 3 minus 2 to the power of 3. So a bit of maths to do, but we can use a calculator, remember. So that gives us 8 factorial over 3 factorial, 5 factorial, 3 to the power of 5 minus 2 cubed. So 8 factorial over 3 factorial, 5 factorial, times 3 to the power of 5 times minus 2 cubed gives us an answer of minus 108,864, and we're done there.
SQA Advanced Higher Maths 2024, Paper 2, Question 9. An arithmetic sequence has the first term minus 3 and a common difference of d. State an expression for the third term. That should be quite easy to start with. So we've got un is equal to a plus n minus 1d for an arithmetic sequence. So the first term is minus 3. So un equals minus 3 plus n minus 1d. And we want the third term, so u3 equals minus 3 plus, well, 3 minus 1 is 2, 2d. So that's part A. Part B says the eighth term is 5 times the third term. So u8 equals 5u3. But we can also write an expression for u8. u8 equals minus 3 plus n minus 1, 7d. So we've got one expression, but we could also use this one, 5 times minus 3 plus 2d. So expanding that out, u8 must equal minus 15 plus 10d. So we've got two expressions for u8, so we can just make them equal to each other to get d. So taking these over here, we get 3d, 15 over there to get 12, and d must be 4, and we're done there. Term algebraically, the least number of terms required so the sum of the associated series is greater than 500. So for 9c, using the start of the exam paper, Sn equals a half n 2a plus n minus 1d. I want to say that that's greater than 500. So we've got a half n, 2a is minus 6 because it's 3, plus n minus 1 times d, and we just worked out d was 4. So that's greater than 500. So we can just keep going. A half n minus 6 plus 4n minus 4 is greater than 500. A half n minus 10 plus 4n is greater than 500. Expanding the bracket out then, a half of 10 is 5, so it's minus 5n. A half of 4 is 2, so it's plus 2n squared is greater than 500. So a quadratic inequality. We get 2n squared minus 5n minus 500 is greater than 0. So we can examine the roots. Now that won't factorise, so there's a, there's b, and there's c. and we'll use the quadratic formula. So x, or in this case n, equals minus b plus or minus the square root of b squared minus 4ac over 2a. So just being careful, we get 5 plus or minus the square root of 25. 4 times 500 is 2,000, times 2 is 4,000, and it's plus because it is minus minus. So that's 5 plus or minus the square root of 4,025 over 4. And you'll just need to get a calculator for that one. So 5 plus root 4025 divided by 4 is 17.1, or 5 minus root 4025 over 4 is minus 14.6. Now let me just draw a graph for this. We want it to be greater than 0. So we've got 17.1 over here, and we've got minus 14.6 over there. So you can see if it's greater than 0, either less than minus 14.6 or greater than 17.1. But we can eliminate this one because n has to be bigger than 0. The solution is n is greater than, strictly greater than, or equal to 18. Or you could say that n is greater than 17 if you prefer. So to answer the question, determine algebraic the least number of terms required so the sum of associated series is greater than 500. Least number of terms is 18. It's not 17. And we're done there.
X plus 5, 3x plus 2, and 5x minus 1, where x are a member of the natural numbers. So the first 3 terms form the start of an arithmetic sequence. Okay, let's start doing that. So let's say x plus 5 is u1. 3x plus 2 would be u2, our second term, and 5x minus 1 would be u3. Let's check the common difference between each of the terms. So let's do the first two. u2 took away u1. That is 3x plus 2 minus x plus 5. That equals 3x minus x is 2x. 2 take away 5 is minus 3. And then let's check the common difference between the next two terms. u3 minus u2. That gives us 5x minus 1. Take away 3x plus 2. That is 2x minus 3. So since it's got the same common difference, that implies u1, u2, u3 form an arithmetic sequence with A being equal to x plus 5 and D, a common difference being 2x minus 3. Part B, find a simplified expression for the 15th term of this sequence. So un, remember, equals A type plus n minus 1 D. And we've already know that A equals x plus 5. D is 2x minus 3. And n is the 15th term, so 15. So we get u15 equals x plus 5 plus 15 minus 1 times 2x minus 3. So u15 equals x plus 5 plus 14 2x minus 3, which is x plus 5 plus 28x minus 3 tens are 30, 3 fours is 12, 42. So u15 must equal 29x minus 37. The sum of the first 20 terms of a sequence is 1, 1, 30. Find the value of x. So remember, the sum is n over 2, 2a plus n minus 1d. Okay, so we want to find if we know the sum of the first 20 terms of a sequence. So that's 20 over 2. 2 times a, but remember a is x plus 5. Plus n minus 1, or just 19, times our common difference, which is 2x minus 3. Okay, so that implies we've got 10 on the outside, 2x plus 10 plus 38x minus 57. So that's 10 times 40x minus 47. That's 400x minus 470. And remember that equals 130. Should have divided by 10 first, but never mind. So we've got 40x minus 47 is 113. That gives us 40x equals a nice round number of 160, which implies that x must be 4. SQA Advanced Higher Maths 2024, Paper 1, Question 3. A geometric sequence has positive terms and SQA Advanced Higher Maths 2024, Paper 1, Question 3. A geometric sequence of positive terms has the third term 36 and the fifth term 16. Find the common ratio. So a geometric sequence goes AR squared, AR cubed, and so on. So AR squared is 36. And similarly, AR cubed, AR4 must be 16. Where R is the common ratio, so we just divide them together. AR4 over AR squared is 16 over 36. And 4 goes into both of them. 4 4s is 16 and 4 9s is 36. So dividing that through, R squared is 4 ninths, which means that R is equal to the square root of 4, which is 2, over the square root of 9, which is 3. 2/3, and we're done there. Part B says, calculate the value of the first term. Well, the first term is A. So just using AR squared equals 36. A times 4 ninths, because that's R squared, equals 36. So A equals 36 divided by 4 ninths. 36 times 9 quarters. Well, 4 nines is 36, so that's 9 times 9, which is 81. So the first term is 81. And then the last bit says, C, state why it has a sum to infinity. Well, this was B, by the way, and that was A. C, it has a sum to infinity because minus 1 is less than 2/3, which is less than 1, in other words. So that's all you need to say. Question D. I'll just put therefore the sum to infinity exists. Question D. Find the value of the sum to infinity. So the sum to infinity for this sort of sequence is A over 1 minus R. So A is equal to 81 over 1 minus 2/3. 81 divided by 1/3. That's 81 times 3 then. 3 ones is 3, 3 eighths is 24, 2, 4, 3, and we're done there. SQA Advanced Higher Maths 2023, Paper 2, Question 8. The fourth and seventh terms of a geometric sequence are 9 and 2, 4, 3 respectively. Find the common ratio and the first term. So we know the fourth term. So for part A, we can say that U4 equals 9. And then we know later on U7 equals 2, 4, 3. But what does that actually mean? Well, remember, if it's a geometric sequence goes A, and then it's A times R squared, A times R cubed, and so on. So the fourth term is AR cubed, and the seventh term will be AR to the 6, 1s. So we can divide them together. So if we do u7 over u4, that's the same as doing 243 over 9, but that will equal AR6 over AR cubed. So 243 divided by 9 is 27. A's cancel and that gives you R cubed. So that means that R must equal 3, because 3 3s is 9 times 3 is 27. R equals 3. And then we just sub in, so AR cubed equals 9. So A times 3 cubed equals 9. So A is 9 over 3 cubed, which is 9 over 27, which is a third. So we get 1/3 for A and 3 for R. So that's part 1 done, and part 2 was the first term, so that's that done. So for part B, Sn, remember, from the start of the exam paper, equals A 1 minus R to the n over 1 minus R. Well, we know our A is a third. We know what R is 3. So we've got Sn, we can put S2n then as A 1 minus R to the 2n. Well, what does that give me for Sn? Sn equals a third, 1 minus R, which is 3 to the n, over 1 minus 3. That's 1/3, 1 minus 3 to the n over minus 2. So what about S2n? Well, S2n is 1/3, 1 minus 3 to the 2n, all over 1 minus 3, which is 1/3, 1 minus 3 to the 2n over minus 2. We have to divide them together, S2n over Sn. So I've got 1/3, so I'll just change that to over minus 2 is 6. So I'll change that to 1 minus 3 to the 2n over minus 6 divided by 1 minus 3 to the n over minus 6 as well. So that's 1 minus 3 to the 2n over minus 6 times minus 6 over 1 minus 3 to the n. So we can then say, well, the minus 6's cancel to give us just 1 minus 3 to the 2n over 1 minus 3 to the n. So now we can, what does 1 minus 3 to the 2n? Well, that is 1 minus 3 to the n, 1 plus 3 to the n. So it's like a difference of 2 squares, because 1 times 1 is 1, and then 3 to the n and 3 to the n is 3 to the 2n, and then the middles will cancel. So it's a little bit of a trick there. But that means I can cancel 1 minus 3 to the n from the top and bottom to just leave 1 plus 3 to the n, or 3 to the n plus 1. And that's what we'll require, 1 plus 3 to the n. So we're done there.
SQA Advanced Higher Maths 2024, Paper 2, Question 7. Find and simplify the Maclaurin expansion up to including the x cubed term for e to the 2x, sine 3x, and then you have to do something together with that. So let's just do part 1 first. Now, you might have memorised e to the x already, but if not, just start from the start. So we've got f of x is f of 0 plus f dash 0x plus f double dash 0x squared over 2 factorial, of course, plus triple x cubed over 3 factorial, and you could go on like this forever. So we've got e to the 2x, that's f of x. So f of 0 is equal to just 1. F dash x is 2e to the 2x, so f dash 0 is 2. F double dash then is 4e to the 2x, so f double dash is 4, and so on. You'll get 8 again, but we'll just see. So f triple dash 0 is 8. So we can say that f of x is equal to 1 plus 2x plus 4x squared over 2 plus ax cubed over 3 factorial, which is 3 times 2 is 6, plus blah blah blah. We've only got the x cubed. 1 plus 2x plus 2x squared. Divide by 2 to get 4x cubed over 3. And they're done there. This is sine 3x. Again, you might have memorised sine x and just put 3x in, but if not, just start from the beginning. Doesn't take too long. Sine of 0 is 0. That's good. G dash x, 3 cos 3x. So g dash 0 is cos of 0 is 1, so that's just 3. G double dash is going to oscillate. We're going to go back to sine. That's going to be minus 9 sine 3x, which means g double dash 0 is still 0. And the triple dash is minus 27 cos 3x. So g triple dash 0 is minus 27. So now we can sub in, we can say that g of x equals g of 0, which is 0, plus, remember it's up here, g dash 0x, so that's 3x plus 0, that's x squared, and then the x cubed minus 27 x cubed over 3 factorial, which is 6. Simplifying that off, we get 3x, 27 and 6, 3 goes into both of them by 9, x cubed over 2. Oh, I'm happy with that. Part B says, hence find the Maclaurin expansion up for e to the 2 sine 3x up to the x cubed term. Okay, so e to the 2 sine 3x, and we've just done e to the 2x and we've done sine 3x. So that's appearing in there. So if I expand this out, e squared sine 3x we already know. 3x is this up here, 3x minus 9x cubed over 2. That's it as a Maclaurin. So then it's just e to the power 2 of that. Well, imagine that as like a variable x or y. We know e to the 2x from up here, so we can just use that. 1 plus 2x plus 2x squared plus 4x cubed over 3. So that gives me 1 plus 2x, but this is now my x, so 3x minus 9x cubed over 2 plus 2x squared, 3x minus 9x cubed over 2 squared, and 4x cubed over 3, 3x minus 9x cubed over 2 to the 3, and it's over 4 over 3, isn't it? 4 thirds. So then we just try and expand and simplify that. Now remember, you only need to go up to x cubed, so you can know a lot of them. So that gives me 1 plus 6x. 2's cancel, so minus 9x cubed. So I've done that line. Next line, 2, I'll have 3x times 3x is 9x squared, timesing these together, 3 times 9 is 27, over 2 times 2 is 27, so minus 27 x to the 4, which you can just ignore, and then minus, I'll just put 9 over 2 x cubed squared, because you can just ignore that one anyway, and you can ignore that one. So that gives you that to expand, plus 4 thirds. And then you're cubing everything, so you get cubed, and then you get squared, squared, cubed again. So the 3x cubed is going to come in. But then what you'll have is, you will have a term here squared times a term here. And that's always going to be too big. And similarly, when you do that times that, that'll be too big. And then the final answer will be too big. So you can just ignore the rest And if you don't realise that, just write it out. So that gives me 1 plus 6x minus 9x cubed. 2 nines is 18x squared. And 3x cubed, I'll just do this at the side, is 27x cubed. So 27 divided by 3 is 9. 9 fours is 36. So plus 36x cubed. So then simplifying that a little bit with x cubed, you get 1 plus 6x plus 18x squared. 36 minus 9 is 27 plus 27x cubed. And there would be other terms, but we'll just not work them out. And we're done there. Simplifying Maclaurin expansion for e to the minus 4x up to including the term in x cubed, and then hence find the first 4 terms of the Maclaurin expansion of this function. Now, if you've memorised the standard power series for e to the x, then you can just jump ahead and jump straight in. Let's assume you haven't memorised that or forgotten it. You can still use the Maclaurin expansion, which given at the start of the exam paper is this. So clearly from this expansion, we need to find a few things. We need to find f dash 0, f second derivative, third derivative, up to here. So let's just do our derivatives. So we know that for part A, f of x is equal to e to the minus 4x. So f of 0 is equal to 1. F dash x is minus 4 e to the minus 4x. So f dash 0 is minus 4. Second derivative is going to be 16 e to the minus 4x. So our second derivative at 0 is just 16. And third derivative is how far we need to go. Minus 64 e to the minus 4x. I've forgotten x here. So our third derivative at 0 is just minus 64. Substitute into our Maclaurin expansion. So f of x equals f of 0 plus minus 4x plus 16x squared over 2 factorial plus minus 64x cubed over 3 factorial. We can tidy that up. 1 minus 4x. 16 divided by 2 is 8, so plus 8x squared. 3 2s are 6, so you get 64 over 6, which is 32 over 3. And we've done part A. Part B, hence find the first 4 terms of the Maclaurin expansion of 3 plus 2x over e to the 4x. We've got 3 plus 2x over e to the 4x. Well, that's the same as 3 plus 2x times e to the minus 4x. But we already know what e to the minus 4x is. It is this. So that's the same as doing 3 plus 2x times 1 minus 4x plus 8x squared minus 32 over 3x cubed up to the x cubed terms. So we've got 3 minus 12x plus 24x squared minus 32x cubed plus 2x minus 8x squared plus 16x cubed plus minus 64 over 3 x to the 4. And this term is not required, remember, because we only want it up to x cubed. So that equals up to the term in x cubed. We've got 3 minus 12 plus 2 is minus 10x. 24x squared minus 8x squared
is plus 16x squared minus 32x cubed plus 16x cubed is minus 16x cubed. And we don't need anything else. So we're done. There's our final. SQA Advanced Higher Mathematics 2023, paper 2, question 15. A function f of x has the following properties. F dash x is x plus 1 over 1 plus x plus 1 to the 4, and the first term in the Maclaurin expansion of f of x is 1. Part A, find the Maclaurin expansion of f of x up to and including the term in x squared. Let's go with that one then. So for a Maclaurin expansion, we've got f of x is equal to f of 0 plus f dash 0 of x plus f double dash 0 of x squared over 2 factorial, and it goes on, triple dash x cubed over 3 factorial, but we're only up to x squared. So, yep, this is the first term in the Maclaurin expansion is 1, so f of 0 equals 1. Got that information. F dash 0 we can work out. F dash 0, just sub it into the f dash x, is 0 plus 1, which is 1 over 1 plus 1 to the 4, which is 2. So f dash 0 is a half. Suppose we'll need f double dash 0, so we need to find f double dash x. So f double dash x, well, this is a quotient. So we've got v u dash minus u v dash all over v squared. And in this case, we're going to say that our u is equal to x plus 1, which means u dash is equal to 1. And our v is equal to 1 plus x plus 1 to the 4, which means our v dash is equal to 4x plus 1 cubed. So f double dash x, just shoving that in. We've got 1 plus x plus 1 to the 4 times u dash, which is 1, minus u, which is x plus 1, times v dash, which is 4x plus 1 cubed, all over v squared, which we'll just write out and simplify later, but we've got 1 plus x plus 1 to the 4, and that's going to be squared. Now, usually we would simplify the hell out of this, but we're not going to bother because all we're interested in at the moment is f double dash 0, so I might just sub in 0 straight away at this point. So f double dash 0, or f, the second derivative at 0, is 1 plus 0 plus 1 to the 4, so 1 to the 4, minus 0 plus 1, which is 1, times 4 times 1 cubed, which is 1, all over 1 plus 0 plus 1, which is 1 to the 4, which is 1, all squared. So that's 1 plus 1 minus 4 over 1 plus 1 is 2, 2 twos is 4. So that's 1 plus 1 is 2, minus 4 is minus 2 over 4, which is minus a half. Now we can actually say what f of x is a Maclaurin expansion. F of x, remember, is f0 plus f dash 0x plus f double dash 0 x squared over 2 factorial. So subbing everything in, f0, remember, was 1. F dash 0 was a half, so plus a half x. And f double dash is minus a half, so minus a half x squared over 2 factorial. So that gives us 1 plus a half x. A half divided by 2 is a quarter, so minus a quarter x squared. And then it would go on. But there's the first 3 terms. Part B uses substitution u equals x plus 1 squared to find the integral of the function. So we've got the integral of x plus 1 over 1 plus x plus 1 to the 4. Integral of x plus 1 over 1 plus x plus 1 to the 4 dx. And it was us to use the substitution u equals x plus 1 squared. So when u is x plus 1 squared, the u by dx, of course, is going to be 2x plus 1. So we want to know what dx is. So we could take our time on this. So I will take my time. 2x plus 1 dx is du. Or in other words, dx Well, we might as well say x plus 1 dx, because it's x plus 1 on top, equals du over 2. Anyway, we can sub in. So our integral, let's just call this I. Our integral becomes the integral of x plus 1 dx, which is du over 2. We'll just put the half outside. And we've got 1 plus x plus 1 to the 4. So 1 plus x plus 1 is squared is u, so 1 plus u squared. Well, that's handy. Start of the exam paper, the integral of 1 plus u squared, we can use as inverse tan. So that gives us a half times the inverse tan of u plus some constant c. And putting our u back in, that gives us a half times the inverse tan of 1 plus x plus 1 squared plus some constant c. Part C, determine an expression for f of x. We already know that f of x is going to be the integral that we found in part B, which is x plus 1 over 1 plus x plus 1 to the 4 dx. But we've also got some information from the question. We know that f of 0 equals 1. So we know that this is going to equal a half of the inverse tan of x plus 1 squared plus c. So when x is 0, f of x equals 1. So the inverse tan of 1, 45 degrees, that's pi upon 4. So 1 equals a half times pi upon 4 plus c. So 1 equals pi over 8 plus c, which implies that c equals 1 minus pi over 8. So then we can just say that f of x is equal to a half times the inverse tan of x plus 1 squared. Leaving everything as exact value, plus 1 minus pi over 8. And we're done there. For paper 1, question 5. A function is defined as f of x equals x cubed minus x. Determine whether it's odd, even, or neither, and then show that it's got a point of inflection. So part A. If we want to show that it's odd, even, or neither, we're going to have to examine f of minus x. So subbing that in, that's minus x cubed minus minus x. So the minus x cubed is minus x cubed plus x. So minus x cubed plus x, well, what happens if I put a minus here? I get minus x cubed minus minus plus x. So that's equal to minus x cubed minus x, which is minus f of x. So as f of minus x equals minus f of x, we can see the function is odd. And we're done there. Show that a graph of f of x has a point of inflection. So if we're going to get a point of inflection, we're going to examine the second derivative and see whether it's undefined or 0 at some point. So f of x is x cubed minus x. F dash x then, of course, is going to be 3x squared minus 1. F double dash is going to be 6x. So possible inflection when 6x equals 0, so x equals 0. And then we can just examine whether there is a change in concavity or not by just drawing a little table for ourselves. So we're going to go along, either side is 0. So as we approach, so in other words, 0 minus, 0 plus, we're looking at the second derivative here. So just before, when it's minus, well, 6 times a minus number is a minus number, so that's negative. That's 0. And just after 0, like it's tiny little bit, it becomes positive. 6 times positive is positive. So you've kind of got this. So it is a change in concavity. So therefore, change in concavity therefore point of inflection exists. And that's that one done. SQA Advanced Higher Mathematics 2019 Spec, Paper 1, Question 3. A function is defined on a suitable domain by f of x is 3x squared plus 2 over x squared minus 2.
obtain equations for the asymptotes of the graph of f of x. Okay, let's do this. So we've got a denominator of x squared minus 2, so we've got vertical asymptotes. So we can say our vertical asymptotes are when the denominator is 0. Asymptote are when x squared minus 2 equals 0, or when x squared equals 2. So in other words, x is plus or minus root 2. So I'll just like that to be very clear, x is root 2 and x equals minus root 2 are our vertical asymptotes. But it may have non-vertical asymptotes, and if you look here, we can perform division on this. So that's how we find our non-vertical asymptotes. Let's divide. So doing our division, we've got 3x squared plus 2 over x squared minus 2. X squared goes into 3x squared 3 times. That gives you 3x squared, and 3 2s are 6. Take away. 2 minus minus 6 is 8. So we can rewrite f of x as 3 plus 8 over x squared minus 2. Looking at what happens when, should be able to see it's y equals 3 by the way, but you need to kind of have some sort of reason for it. So the equation of a non-vertical asymptote, non-vertical, is y equals 3, since as x goes towards plus or minus infinity, f of x tends towards, we'll just check, it's 3 obviously. If this was massive, 8 divided by something massive, 2 doesn't really come into play here, would give you like, 0. So since f of x, since as x goes to plus or minus infinity, I'm not even going to say f of x, I'm going to say 8 over x squared minus 2 tends towards 0. To show clearly that I know that is happening, so therefore I get 3. And there we are. Determine whether the graph has any points of inflection and justify your answer. Well, to determine points of inflection, we're looking at the gradient of the tangent, so we're looking at derivatives, and usually the second derivative. So let's start off with f of x. So we might as well use this form because it'll be easy to differentiate. So we've got 3 plus 8 over x squared minus 2, f of x. I'm going to get that ready to differentiate, so that is 3 plus 8x squared minus 2 to the minus 1. So the first derivative, well, 3 just disappears, so you get minus 8, x squared minus 2 to the minus 2. But then we need to times by the derivative of x squared minus 2 because of the chain rule, so that's 2x. Tidying that up, that is minus 16x. I'll just shove it back on the bottom, I think. X squared minus 2 all squared. So there's our first derivative. And then we can try and examine the second derivative. So this now has turned into a quotient rule question. So we've got vu dash x squared minus 2 all squared times u dash minus 16. vu dash minus u v dash, which is 2 x squared minus 2 times 2x, because of the derivative of x squared minus 2, all over x squared minus 2 all squared. Let's try and simplify that as best we can. I'll just put a minus 16 in front of there first. A minus times a minus is going to be a plus. We've got 2 times 2, which is 4. 4 times 16 is 64. So 64x squared. X squared minus 2 still. All over x squared minus 2 all squared. Well, common factor on the top is x squared minus 2, leaving minus 16 x squared minus 2 plus 64 x squared all over x squared minus 2 all squared. So we can cancel out one of the x squared minus 2's to leave x squared minus 2 on the bottom. Now, multiplying out our brackets, minus 16x squared on the top, plus 32, plus 64x squared, all over x squared minus 2. Tidying that up, 64 minus 16 is 48. So we get 48 x squared plus 32 over x squared minus 2. So point of inflection would be when the second derivative is 0. So is that ever 0? Well, let's have a look. If f double dash x equals 0, that would imply that 48x squared plus 32 would equal 0, because if you think about it, the whole thing equals 0, 0 times the denominator, assuming. So there you go. Is that ever 0? Well, that would imply that 48x squared equals minus 32. We're not doing complex numbers here, remember. That means that x squared is a negative number, so that's no real solutions. F double dash x is undefined when the bottom of it is 0. So in other words, when x squared equals 2 or x is plus or minus root 2. So it's only undefined at plus or minus root 2. Everywhere else it is defined, and it can never equal 0, and therefore no point of inflection. Oh, we're done there. SQA Advanced Higher Mathematics 2016 Spec Paper 1 Question 13. Functions. Consider the curve in the xy plane defined by y equals 4x minus 3 over x squared minus 2x plus 8. Identify the vertical asymptotes and justify your answer. So vertical asymptotes for part A is when the denominator is equal to 0. So consider x squared minus 2x minus 8 equals 0 when y is undefined. So that means that we can look at this. Minus 4 plus 2. So x equals minus 2 and x equals 4 are vertical asymptotes. If we had an explanation, well, we could just say something like y tends to plus or minus infinity as x tends towards minus 2 and x tends towards 4. And that's all you need to say. Here are two statements about the curve. It does not cross or touch the x-axis. The line y equals 0 is an asymptote. State why 1 is false and 2 is true. So let's deal with them separately. So it says it doesn't touch the x-axis. Well, we'll just consider when it touches the x-axis. That's when y equals 0. So we've got x-axis is when y equals 0. So that is 4x minus 3 over x squared minus 2x minus 8 equals 0. So that implies that 4x minus 3 equals 0, so x equals 3/4. So that's false. It touches it at 3/4. Meets x-axis at x equal to 3/4. Part 2 show that it is true. So you've got 4x minus 3 over x squared minus 2x minus 8. So let's work that out. Y equals 4x minus 3 over x squared minus 2 minus 8. So we kind of want to see what happens as x goes to infinity. So if we can set up some fractions where the x is on the bottom, that would be really handy. So if we just divide the top and bottom through, let's say we had 4, let's say by x squared, yeah? That would be a nice, neat trick. Or we could do partial fractions. So we've got 4 over x then, minus 3 over x squared on the top, all divided by 1. That's an x, remember. So minus 2 over x minus 8 over x squared. And now we can consider, well, what happens as x goes towards plus or minus infinity? So as x approaches plus or minus infinity,
Remember, your fractions essentially disappear. That gives you 0. So y would approach, well, 0 on the top and then just 1 on the bottom, which is just 0. And therefore, the line y equals 0 is a horizontal asymptote. Now, if you don't like that method, or it feels unfamiliar to you, then feel free to start from partial fractions 4x minus 3 over x minus 2 and x plus 4 and make it a over x plus 2, b over x minus 4. Simplify it out, but for this particular spec question, it doesn't come out very well. That's why I've chosen not to do it that way. But you will get them where you've got a denominator in x, a denominator in x, which then tend to 0, and therefore the whole thing tends to 0. So you'll be fine there. SQA Advanced Higher Mathematics 2019, paper 1, question 3. The function f of x is defined as f of x is x squared minus a squared, and the graph is shown. State if it's odd, even, or neither, and give a reason. Well, there's 2 reasons you can give, and I'll show you both. So the first way is just graphically, it's symmetrical about the y-axis. If it's symmetrical about the y-axis, it means that it is even. So we can just say that. F of x symmetrical about y-axis, therefore even. Or we can examine f of minus x. So f of x is x squared minus a squared. So f of minus x is x squared is minus x squared minus a squared. Well, that's the same as x squared minus a squared, which is the same as f of x. So since f of minus x equals f of x, it's even. Either of the 2 options are good for you. Sketch the graph of y equals modulus of f of x. So let's have a quick look at the graph. Y and x. So there's our initial graph there. All that's going to happen is modulus means the size of, so when it becomes negative, it becomes positive again. So between minus a and a, it's exactly the same. So let me just put minus a and a. So it still goes down to a and up at a, but then it just flips upside down. So essentially it just goes like that. And there's no real need to work out that point there because it's not given in the original question. So we're done there. SQA Advanced Higher Mathematics 2017, paper 1, question 12. In the diagram below, the graph of f of x has been omitted. Part of it anyway, not all of it, obviously. The point minus 2, minus 1 lies on the graph, and the line y equals a half x minus 3 is an asymptote. Given that f of x is odd, well, what does that mean? It means it's got half-term symmetry. Or it means that f of minus x equals minus f of x. It says, copy and complete the diagram, including any asymptotes you know to be on the graph. So we know that minus 1, 2 is on the graph. If that is true, f of minus x equals minus f of x, then if I take minus 1, which is 1 in other words, I should get minus f of x, which is minus 2, which is 2. So in other words, I know that 1, 2 is on the graph. Quite simple. So it has to go up 1, 2, and then since because of symmetry, it's got half-turn symmetry, so it must mean that this minus 3 and this 3 give us some symmetry here. And we just kind of need to complete the graph and show the point 1, 2, and we're done there. G of x is the modulus of f of x. On a separate diagram, sketch g of x. Okay, so part B, let's draw a big graph here to show this. We've got x and y. Modulus just means when it's negative, it becomes positive, otherwise it stays as it was. So all of this side is going to stay exactly the same. So 3 was the first asymptote, and we knew it went up at 3. But if you look at your asymptotes as well, since this is going to flip upside down, it's going to go like, it's going to start approaching something else, where it's going to make that also go like that. It's just going to change it, and this asymptote is no longer going to exist because we don't need a negative there's no negative answers, and nothing actually approaches it because it flips up that way. So that asymptote flips that way. So to show that, we can draw, I suppose, a line like that. So the right hand side looks the same as it did before. So we can just have it approaching that side, and then the left-hand side would be approaching that side, and that would be our modulus. And we can put our 2 points on it we already knew before, which was 1, 2, and this one, instead of it being minus 1, minus 2, it becomes minus 1, 2. And we're done there. Question C, state the range of values of f dash x given that f dash 0 equals 2. Part C, state the range of values of f of dash x given f dash 0 is 2. So let's look at back to our graph. You should be able to see that its steepest point is here at 2. It then starts to tail off either side. So the range of values is that f dash x is bounded above by 2. 2 is the biggest it can be. What's the smallest the gradient tangent can be? Well, I suppose what we're looking at here is this asymptote. It approaches these asymptotes, and we know these asymptotes have a gradient of a half. So it's just a half. F dash x is between a half and 2, whereas it never touches a half. So we can say a half is less than f dash x, but it does reach 2 because it says it does, and it was the steepest point. And we're done there.
Advanced Higher Maths 2024, paper 2, question 14. A plane passes through A, B and C. Determine A, B and AC. Reason you through this one, A, B is like higher maths, B minus A. So that is, I'm not going to show the working for this, guys. 1 minus 2 is minus 1. 1 minus minus 1 is 2. Minus 1 minus 8 is minus 9. Okay, AC. C minus A. 4 minus 2 is 2. Minus 2 minus minus 1 is minus 1. 11 minus 8 is 3. So we get our 2 vectors there. Part 2. Hence, find the Cartesian equation of the plane. So we've got a plane. What's a plane? Where's a plane? We've got 3 points, A, some B and C. I don't know where they are, but this will do as a picture. So we've got 2 vectors like that. So we've got a normal to those points at A. So to work out that, it's the cross product. So we do AB cross AC. Now you can use that exam paper for this. It is a matrix, IGK. AB is minus 1, 2, minus 9. And AC is 2, minus 1 and 3. So using this that exam paper to help me, it's the determinant of 2 minus 9 minus 1, 3 times I minus the determinant of minus 1 minus 9, 2, 3 times J plus the determinant of minus 1, 2, 2 minus 1 times K. Our 2D determinants. 2 3s is 6 minus 1 times minus 9 is 9. So 6 minus 9 is minus 3. I. Minus 3, minus minus is plus 18. 18 minus 3 is 15. So it's minus 15J. And then we've got minus times minus a plus. So that's 1 minus 4. 1 minus 4 is minus 3K. But any normal will do. So if I write that as minus 3 minus 15 minus 3, why don't I just take out minus a third as a common factor to get 1, 5, 1, because that's much nicer to work with. Just remembering that we then just do n dot r equals n dot a, b or c, doesn't matter what point you use. I think I'm going to use b because the numbers are easier, 1, 1 minus 1. So I'm just going to use that as my normal because why not, any normal will do. So I've got 1, 5, 1, x, y, z equals 1, 5, 1, and then the point I'm going to use is 1, 1 minus 1. So that gives me x plus 5y plus z equals, let's just work this bit out, 1 times 1 is 1, 5 times 5 is 5, 1 times minus 1 is minus 1, that just equals 5. And there's the equation of our plane. Part B, the line defined by these equations show that the line and plane don't intersect. Let me just copy these equations down to the rest of that page. Okay, I'm going to do this using parametric equation because that's the way I always do something like this. I'm going to let that equal, say, t. And then I get x minus 1 equals t, which implies x equals t plus 1. I get y plus 1 equals minus t, which implies y equals minus t minus 1. And I get z plus 1 equals 4t, which implies that z equals 4t minus 1. So I've got my equations of the line and the point, so I'll just sub them in, and hopefully I'll get a contradiction if it doesn't work. That'll be inconsistent. So I've got subbing in, I get x, which is t plus 1, plus 5y, which is minus t minus 1, plus z, which is 4t minus 1, and that's meant to equal 5, but I'm not going to write equals 5. Just going to sub in to see the point of intersection. Well, that's meant to equal 5, yeah? So we get t plus 1, and we get minus 5t minus 5 plus 4t minus 1 equals 5. Plus 1 is 5t, minus 5t is 0. Then we've got 1 minus 1 is 0, so you get minus 5 equals 5. Well, minus 5 cannot equal 5, so therefore no point of intersection. And we're done there. Vectors, 2017, question 15. A beam of light passes through the points B and T. Obtain parametric equations of the line representing the beam of light. So we've got a beam passing through B and T. So our direction will be in the direction of B to T. So for part A, B to T, we've got T minus B. T is minus 3, minus 22 and 6. And B is 7, 8, 1. So that means we get minus 10, minus 30, and 5, which we can take a common factor out, a fifth of minus 2, minus 6, and 1. Or if you prefer, taking it minus a fifth if you want to make more positive numbers, you would get 1, 6, 2, 6, and minus 1. Whatever way you want. Direction could be going that way, could be going that way. It doesn't really matter, does it? So equivalent to that. So we're going to say my direction is just 2, 6, and minus 1. And then pick a point. The point was B, 7, 8, 1, or T, but B is easy to use, so I'll pick 7, 8, 1. You'll get different answers if you pick the other one, but it's still valid. So now it's easy. X minus 7 over 2 equals y minus a point over the direction equals z minus a point over the direction equals some parameter. I'm just going to call it t. You might commonly see lambda instead. So that means that x equals 2t plus 7. There's your first one. Y is equal to 6t plus 8. And z is, well, minus t plus 1. And we're done there. So that's part A. Part B says a sheet of metal represented by a plane containing the points P, Q, and R. Find the Cartesian equation of the plane. So I'll draw a plane just to give me something to work with, and it contains points P, Q, and R. So P, Q, and R, say. So we've got P to R and P to Q, and our normal will be at right angles to that. So our normal is going to be equal to the cross product of P to R times P to Q. So P to R is minus 3 take away 2 is minus 5, 7 take away 1 is 6, and 1 take away 9 is minus 8. Crossed with P to Q, which is 1 minus 2 is minus 1, 2 minus 1 is 1, and 7 minus 9 is minus 2. So the cross product of two vectors given at the start of the exam paper, it is the determinant of a 3 by 3 matrix. So that is ijk minus 5, 6, minus 8, and minus 1, 1, minus 2. Now, it tells you at the start of the exam paper how to solve this, but it is just pattern recognition. You delete the I columns and you get a 2 by 2 determinant.
You delete the j columns and you get a 2 by 2 determinant, and you delete the k columns and rows and you get a 2 by 2 determinant. So that gives me the determinant of 6 minus 8, 1 minus 2 times I, and then you always take away the j one. So that's minus 5 minus 8 minus 1 minus 2, and then you add the k1, which is minus 5, 6 minus 1, 1. So the determinant of a 2 by 2 matrix times m, take away times m. So that gives me minus 12 plus 8 is minus 4i. And then we've got 10 take away 8, which is 2, so minus 2j. And then we've got minus 5 plus 6 is 1, so plus k. In other words, minus 4, minus 2, and 1. So that's our normal. So then n dot r equals n dot a, where r is just x, y, z. So that gives me minus 4, minus 2, 1, x, y, z equals minus 4, minus 2, 1. And our point A, well, A is just our point P, which is 219. So minus 4x minus 2y plus z equals the dot product. That times that is minus 8, minus 2 is minus 10, minus 10 add 1 is, well, minus 10 add 9 is minus 1. Probably make that look a little bit neater by switching some signs here. 4x plus 2y minus z equals 1. And we're done there. Question C. The beam of light passes through a hole in the metal at point H. Find the coordinates of H. So we've got our plane, a sheet of metal, and we've got the equation of that. We've got the equation of a line, so we'll just substitute it as a point of intersection. So where's our equation? Oh, there's our parametric equations. Let's just copy them down. So we've got our plane, we've got our equations for the line, so we'll just sub in. So we've got 4, 2t plus 7, plus 2, 6t plus 8, minus z, so minus t add 1, and that all equals 1. Expanding the brackets, we've got 8t add 28, add 12t, add 16, plus t minus 1 equals 1. Collecting the terms, 12 and 8 is 20, and 1 is 21 t's. And then we've got 28 plus 16 is 38, 44, minus 1 is 43. So plus 43 equals 1. So that means that 21t is equal to 1 minus 43, which is minus 42. So t is minus 2. So we've got our t now, so now we need to sub that back in to these equations here to get our point. So we'll just sub that in, so x is equal to minus 4 add 7, which is 3. Y is equal to minus 12 add 8, which is minus 4. And z, minus 2 is 2, plus 1 is 3. So our point of intersection is simply 3, minus 4, and 3. And we're done there. Vectors SQA Advanced Higher Mathematics 2019 question 15. The equations of two planes are given as pi 1 and pi 2 below. 2x minus 3y minus z is 9, and x plus y minus 3z is 2. Therefore, the line of intersection of these two planes has parametric equations as follows. So easy way to just sub them into each plane and just see that you get 9 and 2. And that's it. So let's just check. So for pi 1, we've got 2 lambda plus 3. Minus 3 lambda minus 1 minus lambda. Well, that equals 4 lambda plus 6 minus 3 lambda plus 3 minus lambda. 4 lambda minus 3 lambda is lambda, minus lambda is 0, 6 plus 3 is 9, and therefore L1 is on pi 1. Okay, pi 2. So we've got x plus y minus 3z is 2, x
plus y minus 3z, 2 lambda plus lambda is 3 lambda minus 3 lambda 0, 3 minus 1, that equals 2. Therefore, L1 is on pi 2 as well. And we're done there. Part B. Let pi 3 be a plane with equation minus 2x plus 4y plus 3z equals 4. Calculate the angle, acute angle, between the line L1 and the pi 3. So a bit of higher maths extended here. Let's have a look. Just copy that question over so we can all see it. Copy the question over and the information from the previous question about the equation of the line. Our vector end or R, remember, so our normal we can get straight away is minus 2, 4 and 3. And then we've got our point of x, y and z. So from that point, that's written as parametric, remember, but we can switch that into non-parametric. So we can say we've got x minus 3 over 2 equals y plus 1, well, over 1, which equals z minus 0 over 1, and that equals some lambda. So we've got our normal, which is minus 2, 4, 3, and then we've got our other direction, which is the bottom of this, which is 2, 1, 1, which in future, if you want, you can just get from the coefficients of lambda. So our direction is 2, 1, 1. So there's our two vectors. So cos theta we need to find. So it's the dot product over the modulus. So the dot product, well, that's minus 4 plus 4 is 0 plus 3. That's just 3 then. Over the size of n. Well, that's the square root of all these added up. So let's just do that. 3 3s is 9, 4 4s is 16, that's 25. 2 2s is 4, that's 29. So we get 29 for one of them. And the other one, 2 2s is 4, 5, 6. So we get root 6. So this will be a calculator question, of course. So we work out our theta by doing the inverse. Just leave it in degrees. 3 divided by root 29 times root 6, 76.854. Let's call it 9 degrees. But since it's an angle between the line and the plane, remember that's the one where you need to work out the complement. So actually you need to take off a 90. So that means that our angle is actually equal to 90 minus 76.9, which is about 13. 13.1 degrees, or 13 degrees if you prefer. Or you could have left your answer in terms of radians, and that would be fine too. Question C says L2 is the line perpendicular to pi 3 passing through the point 1, 3, minus 2. Determine whether L1 and L2 intersect. So I suppose we're going to need the equation of L2 and then simultaneous equations with L1. Okay, so I've taken a note of all the information that we need from that, pi 3 and L1. So let's have a look at the equation of the line L2. So it's perpendicular to this. So if we look at our direction for L2, we've got minus 2, 4, and 3. And I've got a point which is 1, 3, and minus 2. So we can again write down the equation in terms of x, y, and z parametrically. So direction and point means that we can say that x equals minus 2. What letters did I use up here? Did I use t's? Yeah, so let's use a different letter. Let's say minus 2 mu plus 1. Y equals 4 mu plus 3.
z equals 3 mu minus 2. And there you go, we've got three equations. And we've also got three equations here. So now we need to solve them simultaneously. So we'll equate the x's, the y's, and the z's together. So looking at our x's, that gives minus 2 mu plus 1 equals 2 lambda plus 3. Looking at our y's, 4 mu plus 3 equals lambda minus 1. And looking at our z's, 3 mu minus 2 is equal to lambda. So we're able to solve two equations simultaneously. So let's just take the top two. So let's make the lambdas the same. So let's times that by 2. Eight mu plus 6, 2 lambda minus 2. So we can take them away from each other. Minus 2 minus 8 is minus 10. 1 minus 6 is minus 5. The lambdas cancel. 3 minus minus 2 is 5. So we get minus 10 mu is equal to 10. So mu is minus 1. So now we know that mu is minus 1. So we need to find lambda. So we can sub that back into any equation. So let's just sub that back into the x equation. So from x, minus 2 mu plus 1, we get minus 2 minus 1 plus 1 equals 2 lambda plus 3. 2 plus 1 is 2 lambda plus 3. So 3 equals 2 lambda plus 3. So 2 lambda is nothing. So lambda is nothing. So we now know that for the first two equations, mu is minus 1 and lambda is 0. But does that work for the third equation? Because if it does, then they intersect. And if it doesn't, it doesn't. So our third equation was 3 mu minus 2 is lambda. So from z, 3 mu minus 2 is lambda. So looking at our left-hand side of that, we get 3 times minus 1 minus 2, which is minus 5. And looking at our right-hand side of that, well, that's just 0. Well, minus 5 does not equal 0. So that is like an inconsistency there. So the lines don't intersect. And we're done there. Vectors SQA Advanced Higher Mathematics 2018, question 16. Planes pi 1, 2, and 3 have those equations. Three equations, it's probably going to be Gaussian elimination. Use Gaussian elimination to find the value of A such that the intersection of the planes is a line. Let's just set up our matrix then. So question A, we have got 1 minus 2, 1 equals 4. We've got 3 minus 5 minus 2. And then that gives me 1. And then finally, minus 7, 11a. And that gives me minus 11. So that matrix work, we need to get the lower triangle to be 0. So I'm going to say that straight away row 3 becomes row 3 plus 7 row 1. And I'll do the other row 2 as well. Row 2 becomes row 2 minus 3 row 1. So we've still got 1 minus 2, 1 and minus 4. And then we've got 3 minus 3 is 0. Minus 2 plus 6. Minus 5 plus 6 is 1. Minus 2 minus 3 is minus 5. And 1 plus 12 is 13. And then we do row 3. Minus 7 plus 7 is 0. 11 minus 14 is minus 3. A plus 7 is A plus 7. And minus 11 and 7 fours is 28. So minus 28 is minus 39. So we get there quite quick. So I'm going to say that row 3 becomes row 3 plus 3 row 2. So I've got 1 minus 2, 1 minus 4, 0, 1 minus 5, 13, 0, 0, and then a plus 7 minus 15 is a minus 8. And minus 39, well, 3 13s is also 39, so that gives me 0 there, that's nice. And therefore, a equals 8. Part B. Find the equation of the line of intersection of the planes when a takes this value. So we've already worked out that a is 8 for this to get 0, 0, 0, 0. And therefore, for part B, we just introduce some parameters. So let's just say that z equals t for the sake of argument. So that means that from our second row, y minus 5t equals 13. Or in other words, y is equal to 5t plus 13. And then from our third row, we've got x, or first row even, minus 2y plus z, which is t, is equal to minus 4. But we know what 2y is 5t add 13. And we know what z is, that's t. So we get x minus 10t minus 26 plus t is minus 4. X minus 9t minus 26 is minus 4. So finally, x is equal to 9t minus 4 add 26 is 22. So there's our x, there's our y, there's our z. Question C. The plane pi 4 has that equation. Find the acute angle between pi 1 and pi 4. So there's all the information we need for part C. Find the acute angle means we need to find the angle between the normals. So normal 1, say, or I'll call it normal 4 for consistency's sake, is minus 9, 15, 6. Coefficients of x, y, z. And normal 1 is 1, minus 2, and 1. So we need to do them. Cos theta then is equal to the dot product over the modulus. So the dot product, remember, is just times them and add. So that's minus 9, minus 30 is minus 39, add 6 is minus 33. Now I've started sort of finished, but you could have actually simplified that to get a easier number to deal with, because you could have had a multiple of the normal, but that's fine, doesn't matter. Unless it's non-calculative, it might. Nah, it's got a calculator, who cares? Okay, so over the square root of two numbers. So I've got 9 squared plus 15 squared plus 6 squared, which is 342. And then 1 squared is 1, 2 twos is 4, 1 squared is 1, 4, 5, 6. So then we just do our inverse cos. And let's do the inverse cos of 33 over root 342 times root 6, which is 43.28 degrees, 43.2. Cast diagram. Cos is negative here and here, so theta is 180 minus 43.2, which is 136.8. So since we want the acute angle, you can imagine this is between two planes. You'll have an angle one side and an angle the other. You can just take it away for 180, but to get back to acute angle. So the acute angle is simply 180 minus 136.8, which we already know is 43.2. And we're done there.
Describe a geometrical relationship between pi 2 and pi 4. Well, let's have a look at pi 2 and pi 4 then. So there's a pi 2 and pi 4, and we have to describe a geometrical relationship. So let's have a look at the normals. The normal of pi 2 is 3 minus 5 minus 2. And the normal of pi 4 is equal to minus 9, 15, and 6. Well, if you look at that, 3 3s is 9, 3 5s is 15, 3 2s is 6. So we can write n4 as equal to a multiple of n2. So let's just write what that multiple is. First of all, it'll be minus 3, minus 9, 15, 6. So since n4 is a multiple of n2, then pi 2 and pi 4 are parallel. And that's it. We're done there. This has been Clelland Maths. Hope you found this useful. It's went through every single topic, question by question by question, for the maths exams in 2025. Take care, stay safe, and goodbye.